Most people think of the universe as a sea of galaxies, stars, and bright light blasts, but that's not how it really is. The truth is that more than 80% of the universe is made of nothing. Huge voids that run for hundreds of millions of light years and are colder and emptier than anything we can think of. As you look inside, you won't find many planets or stars. It's very quiet. There are no gaps between these structures. They show the real face of the world. One day, these gaps will be the only things left. It is this trip into the cold nothingness that will decide the course of our cosmic future. Mapping the Great Nothing. People have thought of the night sky as being full of stars, galaxies, and unending brightness for millennia. However, astronomers found something disturbing when they eventually figured out how to map the universe on its biggest scales. It is not crowded. Most of it is deserted. Our perception of galaxies dispersed over space is not accurate. Galaxies create narrow walls and filaments around enormous bubbles of emptiness in the actual universe, which is a gigantic black latticework. The bulk of the cosmos is composed of these bubbles, which are known as cosmic voids. The first hints of this came in the mid-20th century, when astronomers began large-scale galaxy surveys. Using telescopes to record thousands of galaxies and then plotting their positions, they expected to see a relatively uniform distribution. Instead, the maps showed clusters, filaments, and then blank regions, entire stretches of space where almost no galaxies existed. By the 1980s, surveys like the CFA Redshift survey revealed the first three-dimensional slices of the universe, showing unmistakable gaps. For the first time, humans were truly mapping the Great Nothing. These discoveries were shocking. Space had always been assumed to be sprinkled with galaxies evenly, like stars across the sky. But the maps looked more like a sponge or a foam, with glowing walls of galaxies surrounding yawning voids. Emptiness wasn't a rare feature, it was the dominant feature. Today, we know that about 80% of the universe's volume is made of these underdense regions. What we think of as the universe, the galaxies, clusters, and walls, are just the thin scaffolding around them. Consider the cosmos as a vast cosmic network to better understand this. The filaments, which span hundreds of millions of light years, are composed of galaxies that are gravitationally bonded together. Massive clusters arise when threads meet. However, there are enormous spaces between the knots and the threads, areas so barren that whole galaxies can float inside them without any companions. When it comes to cosmic topography, these gaps are the real rulers. Mapping them isn't easy. Galaxies shine, but emptiness does not. To chart a void, astronomers must first record where galaxies are, then measure where they aren't. This means building huge surveys of the sky, sometimes cataloging millions of galaxies, then analyzing the gaps. Modern projects like the Sloan Digital Sky Survey, SDSS, and the Dark Energy Survey have refined this technique, giving us the most detailed maps of cosmic voids ever produced. These maps show that voids can be enormous, stretching hundreds of millions of light years across, and that they are interconnected, forming a bubble-like structure that dominates the universe. But how empty are these voids? The answer depends on scale. On average, voids contain fewer than one galaxy per 10 million cubic light years. In some of the largest, you could travel for hundreds of millions of light years and encounter only a handful of galaxies. Even more striking is the density of atoms. While intergalactic space in general has about one atom per cubic meter, voids can have one atom per 10 cubic meters or less, so empty that, in practical terms, it is nearly a perfect vacuum. This mapping has important consequences. Cosmologists discovered that the structure of the cosmos is not random by examining voids. The mechanics of the Big Bang and the ensuing struggle between dark energy and gravity are reflected in it. The history of cosmic expansion is encoded in the dispersion of filaments and voids. Since the expansion and growth of voids directly reveal information on the acceleration of the cosmos, mapping voids has really emerged as one of the most effective methods for examining dark energy. There is also a philosophical weight to the discovery. When people imagine the universe, they picture galaxies stretching endlessly in every direction. But the truth revealed by mapping is far lonelier. Galaxies are rare. They huddle together in thin walls, leaving the rest of space barren. The night sky's abundance is an illusion created by distance. The true universe is defined not by what is there, but by what isn't. The maps of voids and filaments appear uncannily similar when viewed from a distance, like the neuronal connections in a brain or a cross-section of foam. However, these structures are hundreds of millions of light-years broad, rather than neurons or bubbles. They serve as a reminder that nothingness is structure rather than absence. The architecture of the cosmos includes voids just as much as galaxies. There would be no web, no walls, and no clusters if there were no voids. Nothing is as much a part of the cosmos as anything is. The Bootes Void, the Giant's Hollow. A hole in the universe was discovered in 1981 by astronomers cataloguing galaxies in the constellation Bootes. This discovery was so shocking that it completely changed our understanding of the world. At an astounding 330 million light-years vast, this area, now called the Bootes Void, is among the biggest voids known to exist. To put that into perspective, even light moving at 300,000 kilometers per second would take more than 300 million years to span the Milky Way if it were positioned at one edge. It is a void so vast that it has been dubbed the Great Nothing, and it is more than simply a gap. At first, the discovery was hard to believe. Astronomers expected voids to exist, but not at this scale. The Bootes Void is so large that it makes galaxy clusters look like pebbles scattered around the edge of a canyon. Inside this emptiness, only about 60 galaxies have been identified. By comparison, a region of space that size should contain at least 10,000 galaxies if the universe were evenly filled. The void isn't just underdense, it is almost deserted. Finding galaxies inside the Bootes Void was like spotting campfires in the middle of a desert night. The few that survive are lonely, isolated systems adrift in darkness. These galaxies have no nearby neighbors to merge with, no dense filaments to funnel fresh gas, and little opportunity for star formation. They are galactic hermits, cut off from the bustling hubs of cosmic life. Studying them provides a rare chance to see how galaxies evolve in extreme isolation, like plants struggling in a desert ecosystem. The structure of the void itself is equally fascinating. Its boundaries are defined by walls of galaxies forming the edges of the cosmic web. Imagine a soap bubble in a frothy foam. Where the bubbles meet, matter collects. The Bootes Void is one such bubble, but on a scale so vast that it defies imagination. Its edges mark where filaments of galaxies intersect, while its center is nearly empty. To visualize it, picture the Milky Way's local group swallowed up inside a dark sphere so big that even the entire Virgo cluster, our nearest galactic supercluster, would barely register within it. What caused such a massive hollow? Cosmologists believe the answer lies in the expansion of the universe and the pull of gravity. Over billions of years, matter flowed toward denser regions, leaving behind underdense zones. As galaxies clumped into filaments and walls, voids were emptied out, growing larger with time. The Bootes Void may have begun as a modest underdensity in the early universe, but cosmic expansion stretched it into a chasm hundreds of millions of light-years wide. The sheer size of the Bootes Void has inspired speculation beyond mainstream science. Some early astronomers wondered if it might be evidence of something exotic, perhaps a defect in the fabric of space-time, or even the aftermath of a collision between universes. While these ideas remain speculative, the void continues to push the boundaries of how we think about cosmic structure. It forces us to confront the scale of emptiness and its role in shaping the universe. Despite its desolation, the Bootes Void is not truly empty. Dark matter likely threads through it in faint filaments, too thin to gather visible galaxies. Hot plasma and intergalactic gas may lurk at levels below our detection. And of course, the void is filled with the cosmic microwave background radiation, the faint afterglow of the Big Bang. But compared to galaxy-rich regions, it remains a desert, where visible matter is scarce, and life as we know it seems profoundly unlikely. For astronomers, the Bootes void is a natural laboratory. By comparing galaxies inside it with those in clusters, scientists can test theories of galaxy evolution under extreme conditions. Why do some galaxies manage to survive in such isolation? How does star formation proceed when cut off from external gas? These questions make the void as valuable scientifically as it is dramatic visually. Humans find the Bootes void to be extremely unnerving. Consider a civilization on a planet within one of the galaxy's few remaining galaxies. They would have a tragically empty night sky. They would see virtually nothing, only a few lonesome smudges of light, dispersed over unfathomable distances, in place of the Milky Way band, or thousands of galaxies visible through telescopes. They would perceive the cosmos as a tiny empty space, a frigid desert devoid of any indications of wealth. They could only catch a glimpse of the actual cosmic network by gazing far beyond their nothingness. Why voids exist? Cosmic voids appear nearly strange from the outside. Why would nothingness take up so much room in the universe? Aren't galaxies supposed to be more uniformly distributed, occupying the universe like sand grains? It turns out that the explanation is found in the incessant struggle between dark energy and gravity in the early post-Big Bang era. Voids are unavoidable byproducts of the universe's evolution, not errors. The story begins nearly 13.8 billion years ago. In the first fraction of a second after the Big Bang, the universe underwent a period of rapid inflation, expanding faster than the speed of light. Tiny quantum fluctuations, imperceptible ripples in density, were stretched to cosmic scales. These fluctuations became the seeds of structure. Regions that were slightly denser in matter pulled more material toward themselves, while regions that were slightly emptier lost material to their surroundings. Over billions of years, the dense spots grew into galaxies and clusters, while the empty spots expanded into voids. This process is sometimes called gravitational instability. Imagine a field of hills and valleys. The hills attract more snow, growing taller. The valleys, already a little lower, get left behind, becoming emptier. The same thing happens in the cosmos. Dense regions became denser, pulling in matter. Underdense regions became emptier, losing matter. The result is the foam-like structure of the universe, filaments and walls surrounding giant voids. But gravity alone doesn't explain everything. In the past 5 billion years, dark energy has become the dominant force in the universe. Dark energy accelerates cosmic expansion, and it has a particularly strong effect on voids. Because voids are underdense, they have less gravity to resist expansion. As a result, they grow faster than the universe itself. Matter flows out of voids into surrounding walls, leaving them even emptier. The Bootes void, for example, didn't start out 330 million light-years wide. It grew that large because dark energy stretched it faster than the cosmic average. This makes voids a kind of anti-gravity zone. They don't repel in a literal sense, but their underdensity creates an outward push relative to denser regions. Galaxies near the edge of a void can be tugged away, as though the void is pushing them into the walls of the cosmic web. In this way, voids aren't just passive gaps. They actively shape how galaxies move and how structures form. The idea that voids are the rule rather than the exception is among the most peculiar ramifications. According to surveys, voids make up over 80% of the universe's volume. A thin skeleton surrounds galaxies, clusters, and superclusters. We are concentrating on the brilliant traces and neglecting the dark areas when we think of the cosmos as being full with galaxies. The opposite is true. Galaxies are the uncommon embellishments on the nothingness that dominates the cosmos. So why do voids exist? Because the universe is dynamic. Matter clumps, gravity pulls, and expansion stretches. Without voids, there could be no filaments, no clusters, no structure at all. The emptiness gives shape to the fullness, just as valleys give meaning to mountains. In fact, the very existence of galaxies like the Milky Way is tied to the presence of voids around them. Without empty space to channel matter into walls, galaxies might never have formed in the first place. Voids also provide a unique window into the nature of dark energy and dark matter. Because they expand faster than average, their shapes and sizes are sensitive to the physics driving cosmic acceleration. By studying how voids grow and cluster, astronomers can refine models of dark energy. Likewise, simulations of dark matter filaments show that voids are not completely empty. They contain faint, invisible threads of dark matter linking the walls. Mapping voids helps us trace this hidden skeleton of the universe. Realizing that voids are unavoidable is unsettling. The apparent abundance of the night sky is a delusion of remoteness. Galaxies reside on narrow walls enclosing enormous deserts, as may be seen if we zoom out far enough. As a reminder that even our cosmic neighborhood has its own empty canyon, our own Milky Way is located close to the border of the local void. Voids exist because the universe doesn't grow evenly. It exaggerates small differences until they become enormous structures. The result is a cosmos that looks like lace with glowing threads wrapped around yawning gaps. Far from being accidents, voids are the natural byproducts of gravity and expansion, the negative space that makes the universe's structure possible. The coldest places in the universe. Space is frequently thought of as being cold and chilly. However, because of the cosmic microwave background radiation, CMB, the majority of the cosmos really maintains a constant background temperature of around 2.7 Kelvin, which is only a few degrees above absolute zero. Every nook and cranny of the universe is filled with that subtle light that was left over from the Big Bang. However, a peculiar phenomenon occurs in the enormous voids between galaxies. The temperature falls somewhat below normal. These locations, which are the coldest known parts of the cosmos, demonstrate how cosmic conditions may be shaped by nothingness itself. The discovery of these cold spots began when astronomers mapped the CMB in exquisite detail using satellites like COBE, WMAP, and Planck. Instead of being perfectly uniform, the CMB shows tiny fluctuations in temperature, differences of a few millionths of a degree. Most of these variations come from quantum ripples in the early universe, stretched by inflation. But some cold patches line up with known cosmic voids. That correlation suggests that voids themselves are responsible for cooling the background radiation passing through them. This effect is explained by the integrated Sachs-Wolf effect. As CMB photons travel through a void, they lose a bit of energy. Normally, photons entering and leaving a gravitational well should balance out their energy shifts. But because voids expand faster than the rest of the universe, the balance is broken. Photons leave slightly cooler than they entered, creating cold spots in the CMB map. In other words, the emptiness itself imprints a signature of chill across the sky. The most famous of these is the CMB cold spot, a region of the microwave background unusually cold compared to its surroundings. Some studies link it to the Eridanus supervoid, a void nearly 1.8 billion light-years across. If true, it would make the cold spot the largest single imprint of a void on the CMB ever detected. Though debates continue about whether the void alone can explain the anomaly, the idea that emptiness can sculpt the background radiation of the universe is both strange and profound. So just how cold are these places? The CMB's average is 2.7 Kelvin, but void regions can dip a few hundred microkelvins lower. That may sound tiny, but in physics, such differences are enormous clues. They confirm that voids are not passive gaps, but active participants in cosmic evolution. Their faster expansion doesn't just rearrange galaxies, it literally changes the temperature of the oldest light in the universe. The coldness of voids also extends to their matter content. With so few galaxies and little gas, voids lack the heating sources that denser regions enjoy. Galaxy clusters, for example, glow in X-rays because their hot plasma reaches tens of millions of degrees. Voids, by contrast, are dark and starved. The little matter inside them is thin, cool, and uneventful. In some of the emptiest voids, astronomers estimate that the average particle density is just a handful of atoms per cubic meter. With so little to collide or heat, the voids remain frigid. This makes them natural laboratories for studying the limits of temperature in space. In theory, the lowest possible temperature is absolute zero, minus 273 degrees Celsius, where all motion stops. The universe can never quite reach that, because the CMB ensures a background glow. But voids get as close as nature allows. They are the closest thing we have to natural freezers on a cosmic scale, colder even than the vast majority of interstellar space. It is nearly difficult to picture these areas. Your instruments would register a temperature that is just slightly lower than the cosmic average if you were a spaceship drifting in the center of the Boots void. Your detectors would tell you that you were in one of the world's coldest deserts, even if you wouldn't perceive it immediately since the difference is too subtle for human senses. An area devoid of heat, noise, and nearly all galaxies. Just relax and be quiet. There is more to these freezing locations than just curiosity. They assist astronomers in testing cosmic expansion and dark energy ideas. Researchers are able to compare the data to cosmological model predictions by measuring the amount that voids chill the CMB. A greater or weaker cooling than anticipated might be a sign of novel physics, including changes to general relativity, or even unidentified interactions between dark energy and matter. Galaxies in the desert. Although voids are characterized by emptiness, they are not entirely devoid of life. Rare galaxies, small oases in a cosmic desert, are concealed amid their immense darkness. Cut off from the busy centers of cosmic filaments, these emptiness galaxies are among the most isolated objects in the universe, allowing them to develop in near solitude. To comprehend them is to comprehend the behavior of galaxies when they are deprived of resources, support, and neighbors. The first clue that galaxies could survive inside voids came from surveys in the 1980s. Astronomers expected voids to be nearly empty, with nothing visible inside. But careful mapping revealed faint, scattered galaxies lurking in the middle of these hollows. Unlike cluster galaxies, which swarm together by the thousands, void galaxies often sit tens of millions of light-years from their nearest neighbors. Imagine living in a city where the closest other town is not down the road, but across a continent. That's the kind of isolation these galaxies endure. Their properties are as unusual as their locations. Many void galaxies are dwarfs, small faint systems with only a few billion stars, far less than the Milky Way. Others are irregular, oddly shaped and lacking the elegant spirals or smooth ellipses seen in denser regions. Because they evolve without constant gravitational harassment, they often look primitive, like relics of the early universe. Their isolation has preserved them in forms we rarely see elsewhere. Some void galaxies, however, defy expectations. Instead of being dormant fossils, they sometimes show signs of ongoing star formation. Deprived of the rich gas flows of galaxy clusters, they must rely on their own reservoirs of hydrogen. Surprisingly, many still manage to ignite new stars, albeit at a modest pace. This makes them valuable laboratories. They show how galaxies can sustain starbirth even when cut off from the cosmic web. They are survivors, eking out existence in conditions most galaxies would find impossible. The star-forming void galaxies also tend to be bluer than average. That blue light comes from hot young stars, which burn bright and die quickly. In clusters, galaxies are often quenched, their gas stripped by interactions with other galaxies or the cluster's hot plasma. In voids, however, there is no such interference. Paradoxically, while voids are cold and empty, their galaxies can be livelier than cluster galaxies, forming stars in peace. They are like small villages far from empires, thriving quietly without interference. Yet survival in the desert comes at a cost. Void galaxies often remain small and underdeveloped, never reaching the grand scale of spirals like the Milky Way. Without frequent mergers to build them up, they stay modest. Their isolation protects them from destruction, but also denies them the growth that comes from cosmic interactions. In a way, they are frozen in adolescence, never destroyed, but never allowed to mature into giants. Unexpected lights in the nothingness and enormous spirals discovered in voids are among the most fascinating examples. Despite their seclusion, these uncommon systems have somehow grown in size, perhaps by the gradual accretion of gas from the intergalactic medium. Their existence casts doubt on theories of galaxy formation, by demonstrating that, under the right circumstances, development may occur even in the most barren areas. These enormous creatures are lonesome but majestic desert rulers. Studying void galaxies is scientifically vital. They offer a chance to observe galaxies evolving without external interference, providing a control sample for cosmology. In dense regions, galaxies are constantly colliding, merging, and stripping one another of gas. It's hard to know which processes are intrinsic and which are environmental. Void galaxies strip away that confusion. Their isolation reveals the baseline behavior of galaxies, making them essential for testing theories of star formation, gas dynamics, and dark matter halos. Additionally, observations point to the possibility that empty galaxies have abnormally high amounts of dark matter. Only powerful dark matter halos could keep them together in the void because of their low densities, which make them more brittle. They are therefore great examples to learn about the universe's unseen structure. Even though they have little apparent substance, the fact that they survive at all indicates that their halos are strong. The cosmic web. Physicists anticipated a dispersed distribution, akin to stars strewn haphazardly throughout the night sky when they first plotted galaxies in 3 dimensions. Rather, a cosmic web, a massive linked structure where galaxies form walls and threads while the spaces between them stretch into gigantic voids, was revealed. Our knowledge of the cosmos was revolutionized by this finding. The universe is a network, with voids opening like foam bubbles and filaments burning, not a random sea of galaxies. The web is built from gravity and dark matter. In the early universe, matter wasn't evenly distributed. Tiny fluctuations in density, seeded during inflation, acted like blueprints. Dark matter, invisible but abundant, collapsed into filaments, pulling ordinary matter along with it. Over billions of years, these filaments grew thicker, drawing gas and stars to form galaxies. Where filaments intersect, massive clusters formed, the knots in the web. Between the threads, space was left empty, creating the vast voids that dominate cosmic volume. From a distance, the structure resembles a sponge or honeycomb. Galaxies are the glowing beads along thin strands, while voids are the hollow cavities inside. Surveys like the Sloan Digital Sky Survey, SDSS, have revealed this in breathtaking detail, mapping millions of galaxies across billions of light-years. The result is a portrait of the universe as a network, clusters, filaments, and voids interwoven into a structure that spans the observable cosmos. Voids are the negative spaces of this web, but they are just as important as the filaments. Their growth pushes matter outward, sharpening the filament's edges. In a sense, voids carve the web as much as the filaments build it. Together, they form a cosmic balance, something and nothing working hand in hand. Without voids, the web would not have structure. Without filaments, voids would not have meaning. The size of the cosmic web is staggering. Filaments can stretch hundreds of millions of light-years, with voids in between just as large. The largest structures we know, the Great Walls and superclusters, are all parts of this web. The Hercules Corona Borealis Great Wall, for example, spans 10 billion light-years, a thread so massive it challenges our models of cosmic growth. And yet, even that immense structure is only one strand in the web, one part of a network that extends across the entire observable universe. Simulations help bring this to life. Projects like the Millennium Simulation and Illustris reproduce the cosmic web in computer models, showing how dark matter shaped galaxies into their present form. The results match observations almost perfectly. Galaxies align along filaments, voids swell and expand, and clusters emerge where threads cross. These simulations confirm that the web is not an illusion, but the natural outcome of cosmic physics. For galaxies inside the web, location matters. Those in filaments and clusters evolve rapidly, interacting with neighbors, merging and quenching their star formation. Void galaxies, by contrast, evolve slowly, left to their own devices. This environmental dependence shapes the diversity of galaxies we see today. The web is not just a backdrop, it is an active force dictating how galaxies live and die. Think about being able to view billions of galaxies at once by zooming out far enough. Instead, you would perceive order, gigantic black bubbles of nothingness surrounded by luminous threads that weave throughout space. It would resemble a living thing, a neural network spanning billions of light years, rather than the sky. It has even been referred to as the brain of the cosmos. By some, yet unlike a brain, it is a fixed pattern of time and gravity that does not think. The cosmic web is not permanent, though. The voids will increase and the filaments will narrow as dark energy speeds up expansion. In the distant future, clusters will become isolated islands as galaxies move apart, the threads unraveling. The web itself could eventually disintegrate, leaving only lone giants like IC 1101 to glimmer in the dark. Today's structure represents a snapshot in cosmic history, when the cosmos is at its most interconnected. Supervoids. Supervoids, which are enormous areas so huge that they dwarf even the greatest galaxy clusters, are the monsters among cosmic voids. If cosmic voids are the empty bubbles of the universe, supervoids can be hundreds of millions or perhaps more than 1 billion light-years across, whereas a normal void could only be tens of millions. The cosmos itself appears to be hollowing out in these abysses, which are the deepest in the cosmic web. The idea of supervoids emerged as astronomers pushed galaxy surveys to larger scales. In the 1980s and 1990s, slices of the cosmos from redshift surveys revealed not just small gaps, but enormous underdense regions spanning regions larger than anyone had imagined. One of the most famous examples is the Eridanus supervoid, a colossal structure nearly 1.8 billion light-years wide. Compared to it, the already massive Bout's void is like a small pocket of emptiness. Supervoids matter because of their scale. In regions this large, entire galaxy superclusters are absent. What remains are a few scattered galaxies and threads of dark matter stretched thin across unimaginable distances. If you lived in the center of a supervoid, your night sky would look almost barren. With so few neighboring galaxies, the universe would seem lonely and starved, as if creation had skipped your patch of space. But how do such vast, underdense regions form? The answer lies in the same physics that explains ordinary voids, only amplified. During the universe's early moments, small fluctuations in density set the stage. Some regions had slightly less matter than average. Over time, as gravity pulled material toward denser areas, these underdense regions lost even more. Dark energy then stretched them further, accelerating their growth. A supervoid is simply a region where the initial underdensity was so large that it ballooned into one of the universe's greatest hollows. The presence of supervoids also influences how galaxies move. Because they are so empty, they have less gravity pulling inward. Galaxies at their edges feel the stronger pull of surrounding walls and filaments, effectively being drawn away from the void. This creates the illusion that supervoids push galaxies outward, not by force, but by being zones of weaker gravity. Over billions of years, this repulsion sculpts the large-scale distribution of galaxies across the universe. Astronomers have also connected supervoids to the cosmic microwave background, CMB. As photons from the Big Bang travel through these giant hollows, they lose a small amount of energy, a phenomenon called the integrated Sachs-Wolf effect. This shows up as faint cold spots in the CMB map. The Eridanus supervoid, for instance, may be linked to the CMB cold spot, one of the strangest anomalies in cosmology. Whether the void fully explains it is still debated, but the correlation highlights how even emptiness leaves fingerprints on the universe's oldest light. Detecting supervoids isn't easy. Galaxies are faint and distant, and the emptiness between them is harder to measure than the galaxies themselves. Astronomers use massive surveys like the Sloan Digital Sky Survey to identify regions with fewer galaxies than expected. By comparing these regions to simulations, they can confirm whether they qualify as genuine supervoids. The results reveal that supervoids are not rare. They may account for a significant fraction of the universe's volume, even more than ordinary voids. Supervoids are noteworthy because they put cosmological hypotheses to the test. The mechanics of cosmic inflation, dark matter, and dark energy determine the size and distribution of these hollows. Supervoids may indicate novel physics or perhaps changes to Einstein's general relativity if they are bigger or more prevalent than anticipated. Although the majority of data currently support theory, oddities like the cold spot continue to fuel discussion. Supervoids are the ultimate expression of loneliness. If a civilization arose inside one, it might never realize the true richness of the cosmos. Their telescopes would reveal only a handful of galaxies, scattered thinly across the sky. The cosmic web would seem non-existent, and the idea of a universe teeming with galaxies might never occur to them. For such observers, the cosmos would feel not infinite, but barren. The Eridanus supervoid. The Eridanus supervoid is unique among the known voids in the cosmos because of its immense size and mystique. It is one of the biggest underdense zones yet found, spanning around 1.8 billion light-years. It would take light over 2 billion years to get from one side of the Milky Way to the other, which is longer than sophisticated life has existed on Earth. Not only is this astounding void a record breaker, but it could also be connected to the cosmic microwave background cold spot, one of the biggest mysteries in contemporary cosmology. The cold spot was first noticed in data from the WMAP satellite and later confirmed by Planck. It is an unusually large region of the cosmic microwave background, CMB, that is significantly colder than average, spanning about 5 degrees across the sky. At first, scientists assumed it was simply a statistical fluke, a random low-temperature patch produced by early quantum fluctuations. But its size and depth made that explanation less convincing. Then came the discovery of the Eridanus supervoid, located along the same line of sight. Could the two be connected? The idea hinges on the integrated Sachs-Wolf effect. As CMB photons travel through large underdense regions, they lose a tiny bit of energy due to the faster expansion of voids compared to denser regions. This energy loss shows up as a colder temperature in the CMB. The Eridanus supervoid, being one of the largest ever mapped, seemed like the perfect culprit. If true, it would mean we can literally see the imprint of a void carved onto the oldest light in the universe. But the numbers don't quite add up. Calculations show that the Eridanus supervoid is indeed large enough to affect the CMB, but not enough to explain the full depth of the cold spot. The void can account for some of the anomaly, but not all. That has led to speculation that either the void is more complex than we think, or that something more exotic is at work. Some scientists have even proposed explanations like multiverse collisions or exotic energy fields as alternatives. The cold spot debate remains unresolved, making the Eridanus supervoid a central player in one of cosmology's greatest mysteries. Even without the cold spot, the Eridanus supervoid is remarkable in its own right. Inside its vast expanse, galaxies are extraordinarily scarce. Observations show only a sprinkling of faint systems, each one isolated from others by hundreds of millions of light-years. To live in one of those galaxies would mean looking out into a night sky that feels almost abandoned, with no bright clusters nearby, no rich cosmic web. Just a handful of dim smudges and endless darkness. What makes the Eridanus supervoid so scientifically valuable is its extreme size. Typical voids are tens to hundreds of millions of light-years across. At nearly 2 billion, the Eridanus supervoid is in another category altogether. Studying it helps astronomers understand the limits of structure formation in the universe. Was it simply the product of an unusually large initial underdensity after the Big Bang? Or is its size evidence of something new in cosmology? Supercomputer simulations can produce voids this large, but only rarely. That rarity raises questions. Did we just happen to discover one of the universe's most unusual hollows, or does its existence point to flaws in our current models? The answer could reshape how we think about dark energy, cosmic inflation, or even the geometry of the universe itself. The Eridanus supervoid presents researchers with both opportunities and challenges. Theories of cosmic expansion, dark matter distribution, and the interaction of voids with the CMB may all be tested in this natural laboratory. We may also understand how isolation influences star formation, gas retention, and galactic development by examining the differences between galaxies within it and those in denser areas. For the rest of us, the Eridanus supervoid is simply awe-inspiring. It is the ultimate desert of space, a realm so vast and so empty that words barely capture it. If the Milky Way sat inside, we might never guess that the universe beyond was rich and full. Our telescopes would reveal little but blackness. To us, the cosmos might seem finite and lonely. Only by looking unimaginably far away would we glimpse the walls of galaxies enclosing our prison of emptiness. The local void. When we discuss cosmic voids, they might seem far away, vast voids that are separated from our everyday world by billions of light years. One gap, however, is considerably closer to home. The local void is the name of the enormous, underdense area that is located just next to our own Milky Way. It is the void on our cosmic doorstep, spanning at least 150 million light-years and influencing even the motion of our galaxy in space. The local void was first identified in the 1980s, when astronomers began charting galaxies within about 300 million light-years of Earth. They noticed a peculiar pattern. Galaxies in certain directions were plentiful, forming the walls of familiar structures like the Virgo cluster and the Hydra Centaurus supercluster. But in one direction, behind the Milky Way, there was a conspicuous absence. That emptiness wasn't an observational gap, it was real. The local void had revealed itself not by what was present, but by what was missing. At first, mapping the local void was tricky. It lies behind the plane of the Milky Way, where dust and stars obscure our view of distant galaxies. For a long time, this zone of avoidance made it hard to measure the void's full size. But improved infrared surveys and redshift data confirmed that we weren't just staring into a blind spot. We were staring into a genuine hollow, one that occupies a significant portion of our galactic neighborhood. One of the most important insights about the local void is that it helps explain the motion of the Milky Way. Our galaxy is not static. It moves at hundreds of kilometers per second relative to the cosmic microwave background. Some of this motion comes from the gravitational pull of dense regions, like the Great Attractor, but part of it comes from being pushed by the local void. Because voids are underdense, they exert less gravitational pull than surrounding regions. That imbalance creates what looks like a repulsive effect, nudging galaxies away from voids and toward denser walls. In this sense, the local void is literally steering the Milky Way's path through the universe. Inside the local void, galaxies are scarce, but not non-existent. The few that inhabit its interior are lonely and faint, cut off from the bustling filaments nearby. They provide rare laboratories for astronomers to study galaxy evolution in isolation. Without nearby neighbors to trigger mergers or strip away gas, these galaxies evolve more slowly, sometimes retaining primitive features. They are the cosmic hermits of our neighborhood, glowing faintly in the desert of space. The local void also raises interesting questions about cosmic balance. If so much space near us is empty, why do we live in a galaxy-rich wall at its edge? The answer lies in the physics of structure formation. Matter flows away from voids and into denser regions, where galaxies clump together. That process naturally pushes systems like the Milky Way toward the boundaries of voids. In a sense, our galaxy is perched on the edge of nothingness because that's where galaxies are supposed to collect. Without the void beside us, the local group might not exist at all. Recent studies suggest that the local void may be even larger than originally thought. Its far boundary blends into other voids, creating an interconnected network of hollows. Some researchers propose that it could extend over 200 million light-years, making it one of the largest nearby structures. If true, this would emphasize just how dominant emptiness is in our own cosmic backyard. It's strange to think that we live next to a void. When we look at the night sky, it feels full, billions of stars, thousands of galaxies visible with telescopes. But if you could zoom out far enough, you'd see that we are clinging to a thin wall of matter, with a yawning gulf of darkness stretching beside us. The local void is invisible to the naked eye, but it is as much a part of our environment as the Virgo cluster or Andromeda. It is the silent neighbor that shapes our cosmic address. The long-term destiny of our galaxy is likewise hinted at by the local void. Voids will expand more quickly than barriers as dark energy speeds up expansion. Galaxy separation will increase as the already massive local void expands outward. The local void will engulf everything outside of our region of space in unreachable darkness in trillions of years, when only our local supercluster will be visible. The Hercules Corona Borealis Great Wall. If the immense deserts of the cosmos are voids, then the mountain ranges that surround them are its walls. The Hercules Corona Borealis Great Wall, one of the biggest known structures in the entire universe, is the most enormous of these ranges. It is so vast, spanning an incredible 10 billion light-years, that it calls into question our basic comprehension of the genesis of cosmic scale and structure. Seeing how little even the largest galaxies are in relation to the web that supports them is necessary to appreciate its magnitude. The Hercules Corona Borealis Great Wall was first reported in 2013, when astronomers studying gamma-ray bursts, GRBs, noticed an unusual clustering. Gamma-ray bursts are the most energetic explosions in the universe, often linked to the deaths of massive stars. Because they are so bright, they can be detected across billions of light-years, serving as signposts of distant galaxies. When researchers mapped their positions, they found that many lined up within a massive region spanning nearly a third of the observable universe. This clustering suggested the existence of a truly immense structure, the largest ever detected. Calling it a wall doesn't do it justice. Unlike a solid barrier, the Hercules Corona Borealis Great Wall is a vast network of galaxy filaments and superclusters woven together. Imagine threads of light stretching across billions of light-years, enclosing yawning voids inside. Within this web are countless galaxies, clusters, and filaments, all tied together by dark matter's invisible pull. The wall is not just large, it is so enormous that light from one end would take 10 billion years to reach the other, more than 2/3 the age of the universe itself. The discovery raised immediate questions. According to the cosmological principle, the universe should appear homogeneous and isotropic on the largest scales. In simple terms, zoom out far enough, and things should look evenly distributed. But structures like the Hercules Corona Borealis Great Wall test that principle. If galaxies can clump together into structures this large, is the universe really as uniform as we think? Some scientists argue that such a structure shouldn't even exist under standard cosmological models, which limit coherent structures to about 1.2 billion light-years. At 10 billion, the wall is nearly an order of magnitude larger. How do we explain it? One possibility is that the wall isn't a single coherent object, but rather a series of aligned filaments and clusters that happen to appear connected. From our perspective, these alignments might give the illusion of a continuous structure. Another idea is that cosmic inflation, the rapid expansion of the early universe, could have created density patterns on ultra-large scales, seeding massive features like this wall. Still, the sheer scale leaves many scratching their heads. For galaxies within the wall, life is anything but lonely. Unlike the sparse galaxies in voids, wall galaxies are surrounded by neighbors. Gas flows along filaments, fueling star formation. Clusters collide and merge, creating massive elliptical galaxies. In these crowded regions, interactions are frequent, shaping galaxies in ways that would be impossible in isolation. If voids are the deserts of space, walls like Hercules Corona Borealis are its bustling cities, alive with activity and constant change. The relationship between walls and voids is symbiotic. the Hercules corona Borealis. Great Wall exists because matter drains from surrounding voids into its dense filaments. Without the voids, the wall would not stand. And without the wall, the voids would not be defined. Together, they form the foam-like texture of the universe, where emptiness and substance balance each other across cosmic scales. The Great Wall is almost incomprehensible. We often struggle to grasp the size of our own galaxy, which is only 100,000 light-years wide. Yet here is a structure 100,000 times larger, spanning a distance nearly equal to the observable universe itself. If you placed the Milky Way at one end, by the time light reached the far edge, our galaxy would have aged 10 billion years. Civilizations could rise and fall, stars could be born and die, and still the light would be crossing the wall. The Great Wall of Hercules Corona Borealis is a message about the cosmos, not merely a building. It informs us that the universe is structured on sizes so enormous they defy comprehension rather than being uniform or smooth. It makes us wonder if there is more physics out there, or if our ideas are comprehensive. It serves as a reminder that the vastness of the cosmos may still astound us even after decades of astronomy. Nothing but dark matter? The most striking impression we get when we gaze into cosmic voids is one of absence. No rich swarms of galaxies, no spiral arms, no luminous clusters. However, does emptiness actually imply nothing? Or do these areas continue to conceal something invisible? Cosmologists generally believe that voids are not devoid of anything. Rather, they could be woven together by thin threads of dark matter, an unseen framework that forms even the most empty regions of the universe. Dark matter is the mysterious form of matter that outweighs normal, visible matter by more than 5 to 1. It does not emit or absorb light, but its gravitational pull is undeniable. Galaxies spin faster than their visible stars allow, clusters are held together by unseen mass, and gravitational lensing reveals invisible structures bending light. Without dark matter, the cosmic web would never have formed, and if it pervades the universe so thoroughly, then voids cannot be truly empty. They must also contain their share of this hidden ingredient. Simulations of large-scale structure support this. In computer models like Illustris and Millennium, voids appear as vast hollows in galaxy distribution, but when the dark matter is mapped, they are not completely blank. Faint filaments of dark matter snake through them, thinner and more diffuse than in dense regions, but still present. These filaments form weak connections between the walls of the cosmic web, like the faintest threads in a spider's web, stretched almost to breaking. The presence of dark matter in voids helps explain why the few galaxies that do exist there can survive. In such underdense environments, galaxies would be easily torn apart without strong gravitational halos. The fact that void galaxies remain intact suggests they are cocooned in substantial dark matter halos, providing the glue that holds them together even in isolation. In this sense, dark matter is the quiet protector of galaxies in the desert, giving them structure where visible matter is scarce. But how much dark matter is really there? Observations of voids using gravitational lensing, the bending of light by mass, provide some answers. Even in apparently empty regions, background galaxies' light is subtly distorted. By measuring these distortions, astronomers can estimate how much mass lies along the line of sight. The results confirm that voids contain dark matter, though at lower densities than average. They are not absolute vacuums, but underdense regions where both normal and dark matter are scarce. This brings up a crucial point. Voids are more than just empty spaces. Their density is lower than the cosmic norm, making them areas of relative nothingness. On average, there is a specific amount of mass in a cubic megaparsec of the cosmos, which is around 3 million light-years on each side. That figure is much lower than normal in voids, although it is never quite zero. Faint echoes of structure stretch thin dark matter guarantees that even the deepest voids remain a part of the cosmic fabric. Some researchers speculate that studying dark matter in voids could reveal new physics. Because voids are so underdense, they amplify subtle effects that would be hidden in crowded regions. For instance, Alternative theories of gravity sometimes predict different behaviors in low-density environments. By comparing how galaxies and dark matter behave inside voids, scientists can test whether Einstein's general relativity holds on the largest scales. Voids, ironically, may be the best laboratories for studying the unseen. There is also the question of whether dark matter in voids behaves differently than elsewhere. If dark matter interacts only through gravity, it should spread smoothly. But if it has other properties, like self-interactions or exotic particles, it might leave unique signatures in void environments. Observations of galaxy motion, weak lensing, and cosmic microwave background distortions could all help uncover such effects. As of right now, the image is one of slight perseverance. Dark matter remains, albeit stretched thinner, in voids rather than disappearing. Even though the filaments that cross these hollows might never catch fire from stars, they still weave the universe's structure. A vacuum would not look as an empty sphere if dark matter could somehow be seen. It would glimmer dimly with thin, fragile, but genuine strands of unseen mass. Voids may look like nothingness, but they are not truly nothing. Even in the emptiest corners of the universe, something exists, something unseen, silent, and fundamental. Dark matter fills the gaps, binding the universe together, ensuring that no place is entirely void. How empty is empty? It's simple to picture cosmic voids as complete vacuums, areas devoid of all matter where nothing exists at all, when astronomers refer to them as empty. In actuality, however, even the most arid voids are not entirely empty. How empty they are is a better question. The response illustrates the odd fact that nothing is never truly empty, as well as the startling thinness of matter in voids. In dense regions like galaxies, matter is abundant. The Milky Way contains roughly 100 billion stars, plus gas, dust, planets, and dark matter, all packed into a disk 100,000 light-years wide. Between galaxies, things thin out, but even the intergalactic medium, space between galaxies in clusters, still has a respectable particle density, sometimes hundreds of atoms per cubic meter. By comparison, the best laboratory vacuums on Earth contain trillions of times more particles than the emptiest cosmic spaces. Voids, however, take thinness to the extreme. On average, a typical void may contain only 1 atom per cubic meter, already staggeringly empty compared to anything we experience. But in the largest supervoids, the density can drop to 1 atom per 10 cubic meters, or even lower. To put that into perspective, imagine a cube the size of a refrigerator in your kitchen. Inside, instead of trillions of atoms like in air, there might be only a single hydrogen atom. Everything else would be absent. And yet, even that isn't true nothingness. A single atom per 10 cubic meters may sound negligible, but across the vast expanse of a void, hundreds of millions of light years, that tiny density still adds up to vast amounts of gas and dark matter. It's just so spread out that it cannot collapse into stars or galaxies. Instead, it lingers as an invisible fog, detectable only through subtle effects on light and gravity. By contrasting the average density of the cosmos with the mass density inside a location, observers are able to measure this. A supervoid may have less than 5% of the usual density, whereas a conventional void may have just 10% to 20%. This indicates that while they are significantly underdense in relation to the cosmic mean, they are not total vacuums. The thinness of voids has strange consequences. For example, cosmic rays traveling through them encounter fewer obstacles, allowing them to travel farther before interacting. Photons from distant galaxies pass through voids with little interference, carrying information billions of years across space. Voids are the clearest windows in the cosmos, offering astronomers clean sightlines into the deep universe. Within their rarefied interiors, faint filaments of dark matter thread across, anchoring the few lonely galaxies that survive inside. These filaments are so tenuous that they cannot be seen directly, but gravitational lensing betrays their presence. Without them, even the small galaxies inside voids might fall apart. In this sense, voids are not empty bowls, but delicate spider webs, stretched thin but still real. For comparison, think about the air in a room. At sea level, every cubic centimeter holds about 2.5 times 10 to the 19th molecules. A laboratory vacuum cuts that down to just a few thousand. Outer space near Earth has only a handful of particles per cubic centimeter, but in a cosmic void, the number drops so far that an entire cubic kilometer of space might contain fewer atoms than you take in with a single breath of air. The emptiness is so extreme compared to daily life that ordinary words can barely capture it. And yet, physics tells us that even if you stripped away every atom, the void would not be truly empty. Quantum mechanics ensures that space itself seethes with virtual particles, popping in and out of existence on unimaginably small timescales. This quantum vacuum energy exists everywhere, including voids. So even in the most barren regions, the emptiness is still alive with fluctuations, invisible but essential to the universe's fabric. So how empty is empty? Voids are emptier than any place humans can ever reproduce on Earth. They are emptier than the space between stars, emptier than the gaps between galaxies, emptier than our minds can easily picture. But they are not nothing. They are almost nothing. A thin fog of hydrogen, dark matter filaments, stray photons, and quantum whispers. The sheer scale of this emptiness is haunting. If you were inside a void, you could travel for tens of millions of light years before encountering another galaxy. The night sky would look sparse, almost blank. The sense of isolation would be absolute. And yet, all around you, hidden in the thin fog of atoms and the invisible lattice of dark matter, the laws of physics would still hold sway. The void would feel empty, but never truly be empty. Lonely black holes in the dark. Despite being almost empty, cosmic voids are not inherently safe. According to theoretical theories, wandering black holes, some of the universe's most deadly objects, are dispersed across these enormous hollows. These black holes, which are silent and unseen, remains of long-lost galaxies that were once the victims of cosmic cannibalism, float across the emptiness in contrast to the supermassive giants that anchor galaxies. Where do they come from? One source is galaxy mergers. When galaxies collide, their central black holes often merge as well, but sometimes, during the chaos, a black hole can be flung away by gravitational recoil, a violent kick produced when gravitational waves carry away momentum unevenly. These rogue black holes can be ejected into intergalactic space, destined to wander forever. Over billions of years, some may have drifted into voids, becoming residents of the emptiest places in the cosmos. Galaxies that have been torn apart close to the margins of voids provide another route. Smaller galaxies may be disturbed when matter moves from voids into filaments, causing their black holes to wander. These black holes don't disappear. Instead, they keep traveling in directions that eventually trap them in areas that aren't very dense. The end effect is a population of unseen creatures that roam in areas with few galaxies. But how do we know they're there if they're so hard to see? Direct detection is nearly impossible. An isolated black hole emits no light unless it's feeding. However, astronomers use microlensing to hunt for them. When a black hole passes in front of a background star, its gravity bends and magnifies the starlight, creating a temporary brightening. In 2022, astronomers confirmed the first isolated stellar mass black hole through this method. Extrapolating from such detections, scientists estimate that the Milky Way alone could host hundreds of millions of wandering black holes. Spread across the cosmos, it's reasonable to assume that voids contain their share as well. The scale of these wanderers varies. Some are stellar mass black holes, the collapsed cores of massive stars, weighing a few times the mass of the Sun. Others could be intermediate mass black holes, weighing thousands of suns, kicked out of dwarf galaxies. And some may even be supermassive black holes, ejected from galaxies during titanic collisions, drifting through the void without stars or gas to anchor them. These giants, if they exist in voids, would be among the loneliest objects in the universe. The idea of black holes in voids may sound like science fiction, but simulations suggest it's likely. Supercomputer models of galaxy evolution show that voids are not truly empty. They contain faint filaments of dark matter and the ghosts of disrupted galaxies. Within those threads, black holes could linger, unseen but real. They may drift for billions of years without ever encountering a star or gas cloud to feed on. In that sense, they are cosmic castaways, existing but forgotten. If a wandering black hole in a void did encounter gas, it could briefly flare to life, feeding and shining in X-rays as matter spiraled inward. Such events would be rare but detectable with sensitive instruments like the Chandra X-ray Observatory. Future surveys with instruments like the Vera C. Rubin Observatory may even catch microlensing events caused by void black holes, offering a way to map their hidden population. For astronomers, the existence of these black holes has profound implications. They represent the dark fossil record of galaxy evolution, the leftovers of collisions, ejections, and disruptions. Their numbers and masses could reveal how often galaxies merge, how gravitational waves kick black holes free, and how many galaxies have been stripped away in the growth of the cosmic web. In other words, lonely black holes in voids are silent witnesses to the universe's violent history. Picture yourself already cut off from the rest of the universe and floating across an empty galaxy. An unseen predator may be moving stealthily somewhere in the surrounding darkness, only to be discovered if you ventured too close. It would only devour, it wouldn't shine or warn. The idea of concealed black holes adds an additional element of threat to a world already characterized by nothingness. The expansion within voids. We know for a fact that the cosmos is expanding. However, not all of the universe is expanding at the same rate. In actuality, voids, those enormous, underdense areas that exist between galaxy filaments, grow more quickly than the entire universe. Even though voids are thought of as being empty and motionless, their rapid growth makes them some of the most active locations in the universe. To understand why, we need to revisit how gravity and cosmic expansion interact. In dense regions like clusters, gravity pulls matter inward, resisting expansion. Galaxies within filaments tug on each other, slowing the outward stretch of space locally. But inside a void, there is very little matter to provide that counterweight. With weaker gravity, the force of cosmic expansion has less opposition. As a result, voids stretch out more rapidly, becoming even emptier as galaxies and matter flow away toward denser walls. This phenomenon is sometimes described as voids being repulsive. They don't literally push, but because matter naturally flows from underdense regions into denser ones, galaxies near void edges accelerate away. Over billions of years, this effect sculpts the cosmic web, sharpening walls and filaments while leaving voids hollow. It also means that voids aren't passive gaps. They are active engines of expansion, shaping the universe on its grandest scales. Measurements confirm this accelerated growth. Surveys of galaxies in and around voids show that galaxies on void edges move slightly faster than expected, drifting outward relative to the average expansion. This flow is a direct signature of void dynamics. By comparing these motions with predictions from general relativity, cosmologists can test whether our understanding of gravity holds up in low-density environments. Remarkably, voids offer one of the cleanest laboratories for studying dark energy and modified gravity theories. The growth of voids also explains their enormous sizes. A typical void in the early universe may have been only a few million light-years wide. Over billions of years, cosmic expansion and matter flow stretched it into a cavity hundreds of millions of light-years across. Supervoids like Eridanus, nearly 1.8 billion light-years wide, are extreme examples of this process. Their growth is a natural consequence of underdensity combined with cosmic acceleration. It's surprising that voids can combine. The edges of nearby voids, which are denoted by thin filaments of galaxies, may dissolve as they enlarge. Two voids merge into a single, bigger hollow as those filaments disintegrate. The cosmic web is progressively reshaped by this process, which is known as void percolation. The cosmos eventually becomes divided into enormous linked hollows when small voids merge into bigger ones and the largest take control. Dark energy will hasten this process even more in the far future, leaving behind a world in which nearly all volume is made up of voids. The expansion within voids also leaves imprints on the cosmic microwave background, CMB. Photons traveling through these fast-growing regions lose a tiny amount of energy, appearing cooler when we measure them on Earth. This subtle effect, the integrated Sachs-Wolf signal, has been detected in multiple surveys. It provides direct evidence that voids expand faster than average and confirms that dark energy accelerates that expansion. The cosmos would draw away from you more powerfully if you lived in a galaxy that was located far within a void than if you were in a crowded cluster. Eventually, your closest galactic neighbors may disappear beyond your cosmic horizon as they continue to drift farther and farther away. In a way, cosmic isolation would happen far more quickly for vacuum civilizations. Compared to galaxies in crowded surroundings, they would experience the loneliness of the cosmos sooner. There are significant long-term ramifications. Walls and filaments will thin as voids enlarge. The remainder of the cosmos will eventually turn into an ocean of emptiness, with just the densest clusters remaining linked. The fast expansion of neighboring voids may wipe everything else from the night sky in trillions of years, leaving just the galaxies of our local supercluster. Voids will be the universe in that far-off time period, not merely components of it. So while voids seem empty, they are in fact dynamic. Their faster expansion reshapes the cosmos, accelerates isolation, and gives us unique insights into dark energy. They are the fastest growing structures in the universe, not because of what they contain, but because of what they lack. The gravitational push of nothing. That seems implausible at first. How could nothing push? But when astronomers analyze galaxies close to cosmic voids, they see just that. These enormous areas of nothingness affect motion rather than merely being silent. As if repulsed by the vacuum itself, galaxies near the margins of voids are gently pulled away. The emptiness isn't aggressively pushing, of course. Instead, the outcome feels like a gravitational thrust from nothing because of the imbalance in gravity caused by its lack of mass. To see why, imagine the universe as a landscape of hills and valleys. Dense regions like clusters are the hills, where gravity pulls strongly. Voids are the valleys, where there is little to no pull. If you place a marble on this uneven surface, it naturally rolls away from the valleys and toward the hills. Galaxies behave in a similar way. When a galaxy sits near a void, there is less gravitational attraction on the void side and more on the wall side. The imbalance sends the galaxy drifting outward. To an observer, it looks as though the void is pushing. This phenomenon is crucial in understanding large-scale flows of galaxies. Observations show that galaxies do not simply follow the smooth expansion of the universe. Instead, their motions include additional velocities, sometimes hundreds of kilometers per second, caused by gravitational imbalances. Clusters pull, voids push, and together they create a cosmic dance of movement. The local group, for example, is influenced not only by the pull of the Virgo cluster and the Great Attractor, but also by the push of the local void right next door. The idea of voids repelling matter might sound exotic, but it's grounded in basic physics. Gravity is a relative force. What matters is not just how much mass is nearby, but how it compares to surrounding regions. In voids, where density is far below average, that contrast produces outward flows. Over time, these flows cause voids to grow, as galaxies migrate outward and walls sharpen. The gravitational push of nothing is one of the engines sculpting the cosmic web. Astronomers measure this effect by mapping galaxy velocities with respect to the cosmic microwave background, CMB. Because the CMB provides a universal rest frame, deviations from smooth expansion can be tracked. In many cases, these deviations line up with known voids. For instance, galaxies near the Bootes void show clear signs of outward motion, consistent with the push expected from its underdensity. These observations confirm that voids are not passive emptiness, but active players in cosmic dynamics. This gravitational push can also mimic the effects of dark energy on smaller scales. Both voids and dark energy accelerate separation, but for different reasons. Dark energy drives the overall expansion of the universe, while voids locally amplify that expansion by providing weaker gravitational wells. In this way, voids act like miniature accelerators embedded in the larger cosmic expansion. The push of voids also helps explain why cosmic structures are so sharply defined. Without it, galaxies might smear evenly across space. But as voids push outward and clusters pull inward, matter becomes concentrated along filaments and walls, leaving vast hollows in between. The result is the sponge-like cosmic web we see in galaxy surveys. Emptiness isn't just the absence of structure, it is what sharpens structure itself. Consider living in a galaxy close to a void center. Your few galactic neighbors would drift farther and farther away over billions of years, not because of collisions or explosions, but rather to the void's increased expansion, which pushed them outward. Your cosmos would become more empty and your sky more desolate until only your own galaxy was left to see. It would seem to you that the universe had been physically pushed away by emptiness. The gravitational push of voids also provides astronomers with a unique tool. By measuring how galaxies move around voids, researchers can estimate the void's sizes and densities with surprising accuracy. This makes voids not just curiosities, but essential probes of cosmology. Their expansion and push help refine models of dark energy, gravity, and the growth of structure in the universe. This effect will only worsen in the long future. Voids will grow much quicker when dark energy speeds up the expansion of the cosmos. As their pushes intensify, additional galaxies will be forced out of their interiors, and clusters will be isolated into solitary islands. The walls will disappear, the voids will take center stage, and the cosmic web will shrink. The cold spot debate. The cold spot is one of the numerous mysteries carved into the cosmic microwave background, CMB, that sticks out as being very peculiar. This area of the sky is much colder than its surrounds. It was first identified by the WMAP satellite in 2004 and subsequently verified by Planck. It covers a region of sky 10 times larger than the full moon, with a diameter of around 5 degrees. In addition to being odd, the anomaly could be one of the most perplexing hints regarding the nature of cosmic voids, or possibly the cosmos itself. The cold spot sits in the constellation Eridanus, and its temperature is roughly 70 microkelvins lower than the CMB average. That might sound tiny, but in the precise world of cosmology, it is huge. Most fluctuations in the CMB are only a few tens of microkelvins caused by quantum ripples in the early universe, stretched during inflation. The cold spot, however, is both larger and deeper than expected, making it an outlier in the otherwise well-behaved map of the cosmic sky. One of the most popular theories is that the Eridanus supervoid, a huge void that lies along the line of sight, is what causes the cold spot. The integrated Sachs-Wolf effect causes CMB photons to lose a tiny bit of energy when they travel through such an underdense area. The photons are stretched by the void's quicker expansion, which makes them colder when they get to us. This makes sense on paper since the Eridanus supervoid, which is about 1.8 billion light-years wide, is one of the biggest voids ever mapped. This emptiness would be the one to make an impression on the CMB. But there's a problem. Calculations show that while the void can contribute to the cold spot, it isn't enough. The effect of even a supervoid should only account for part of the anomaly, maybe half of the temperature dip. The remainder is unexplained. This discrepancy has fueled one of the great debates in modern cosmology. Is the cold spot just a rare statistical fluke, or is it evidence of something more exotic? Some researchers argue that it's simply a 1 in 1,000 random fluctuation, nothing more mysterious than an unusual roll of the cosmic dice. If you have enough random spots on the CMB, one will inevitably look strange. Others, however, see it as a crack in the standard model of cosmology. Exotic theories have been proposed. Perhaps the cold spot is the signature of a collision with another universe in a multiverse scenario. Or perhaps it marks an early defect in space-time itself, like a cosmic texture left over from symmetry breaking in the infant cosmos. The debate is fierce because the implications are enormous. If the cold spot is just a void, then it reinforces what we know about large-scale structure. If it's a fluke, then it is a reminder that even a universe obeying simple rules can produce oddities. But if it's something exotic, it could rewrite our understanding of reality, pointing to new physics beyond dark matter and dark energy. Observationally, the evidence is mixed. Galaxy surveys have confirmed the existence of the Eridanus supervoid, lending support to the void explanation. But the void's size and depth still don't fully match the cold spot's features. Alternative analyses suggest that part of the anomaly may indeed be random noise. For now, no consensus exists. The cold spot remains a cosmic Rorschach test. One feature, multiple interpretations. It is unnerving to be in the cold spot. It serves as a reminder that the cosmos has wounds that are difficult to comprehend. Your night sky would already feel empty if you were a resident of a galaxy located inside the Eridanus supervoid. However, your cosmic address may be more odd if that emptiness is also connected to a basic abnormality in the earliest light in the cosmos. You would be living at the center of one of the greatest enigmas in cosmology, not merely in a vacuum. The cold spot debate continues because it sits at the crossroads of two truths. On one hand, voids are real and powerful, shaping cosmic structure and leaving imprints on the CMB. On the other, the cold spot seems too deep to be explained by voids alone. That tension keeps scientists searching, balancing between ordinary physics and extraordinary possibilities. Cosmic microwave background shadows. The afterglow of the Big Bang, a relatively uniform flood of dim microwave radiation that permeates the cosmos, is commonly referred to as the cosmic microwave background, CMB. However, this age-old light doesn't just come at us unaltered. It traverses billions of light-years of cosmic structure, including clusters, galaxies, and most importantly, voids. Additionally, CMB photons leave extremely faint fingerprints, shadows of the voids themselves, as they travel through those enormous underdense areas. This effect is known as the integrated Sachs-Wolf (ISW) effect. It works like this. As photons travel through a gravitational well, like a galaxy cluster, they fall in, gaining energy, and then climb back out, losing it. Normally, the energy gain and loss cancel out. But if the well itself is changing, deepening or flattening as the photon passes, the balance is broken. The photon leaves slightly hotter or colder than when it entered. In dense regions, this can produce faint hotspots. In voids, where the gravitational potential is shallowing as they expand faster than average, photons emerge cooler. The result, the CMB shows faint cold patches aligned with voids, like shadows cast across the oldest light in the cosmos. Detecting these shadows is no easy task. The ISW effect is subtle, amounting to temperature differences of just a few millionths of a degree. But by stacking CMB maps on top of known void positions from galaxy surveys, astronomers can amplify the signal. The result has been clear enough. Voids really do leave imprints on the CMB. The emptiness of today still whispers to us through the light of 13.8 billion years ago. The Eridanus supervoid is among the most well-known instances, and many people think it plays a role in the cold spot phenomenon. However, there are also markings left by smaller voids in the sky. Cosmologists can test dark energy ideas by comparing the intensity of these imprints to expectations. The way dark energy expands the cosmos directly determines how voids expand and impact photons. Because of this, CMB shadows are among the most useful instruments for examining the physics behind cosmic acceleration. These shadows also tell us something profound about the nature of voids themselves. They are not static holes. They are evolving, growing, and reshaping the universe's gravitational landscape. The very fact that they alter the CMB shows that voids are active participants in cosmic history, not just passive gaps. Emptiness, it turns out, is dynamic. From a human point of view, the concept is astounding. Imagine light that has carried the origin of the cosmos with it for about 14 billion years. That light travels across a vast cosmic desert, a gap that is hundreds of millions of light years across. Additionally, the photon's energy faintly cools as it passes through the vacuum. Our telescopes pick up that minute shift after billions of years, which enables us to chart the void's growth and form. In a very genuine way, voids create shadows on time itself, rather than on the ground or walls. The subtlety of these shadows highlights the incredible precision of modern cosmology. The Planck satellite, for example, mapped the CMB with sensitivity so fine it could detect temperature variations of just millionths of a degree. Without that accuracy, the whispers of voids would have gone unheard. Instead, we now have evidence that the largest structures of emptiness can alter the oldest light, tying together the dawn of the universe with its present structure. The shadows also raise questions. If voids can leave measurable imprints on the CMB, could unusually large or deep voids explain anomalies like the cold spot? Some argue yes, though the numbers remain debated. Others suggest that if void shadows deviate from predictions, it might point to new physics, perhaps a departure from Einstein's relativity on cosmic scales. Voids, ironically, could be the places where our theories finally crack. These shadows will disappear as the cosmos gets bigger. Structures will thin, photons will redshift even more, and it will be more difficult to see the imprints. However, as of right now, they continue to represent one of the strongest connections between the early cosmos and the large-scale structure that we observe today. Recorded in the earliest light we can see, they are echoes of emptiness. Galactic outcasts. When galaxies coexist, they flourish. They combine, collide, and exchange gas in clusters and along filaments, sustaining cycles of galaxy expansion and star generation. However, what occurs if a galaxy is trapped tens of millions of light-years away from its closest neighbor in a void? The galactic misfits are these uncommon systems, lonely survivors in the cosmic desert, molded by loneliness in ways we are just now starting to comprehend. When galaxy surveys in the 1980s showed not just the walls of the cosmic web, but also dim stragglers sitting alone in the center of enormous hollows, astronomers first became aware of them. These galaxies were first thought to be unimpressive dwarfs, dark, tiny systems that just happened to wind up in unfortunate locations. However, close examinations showed something more nuanced. Void galaxies frequently differ from their counterparts in denser settings in both appearance and behavior. For one, many void galaxies remain gas-rich. In crowded clusters, galaxies are constantly stripped of their hydrogen by encounters with neighbors or by the hot plasma filling the cluster. Star formation dies out, leaving red quiescent systems. In voids, however, no one is around to take the gas away. Outcast galaxies often retain large reservoirs of cold hydrogen, which allows them to keep forming stars even after billions of years. Paradoxically, the most isolated galaxies in the universe can be among the bluest, their light dominated by young, hot stars. Their shapes also tell a story of isolation. While dense regions are full of massive ellipticals, galaxies puffed up by repeated mergers, void galaxies tend to be smaller spirals or irregulars. Without frequent collisions to disrupt them, they evolve more gently. Some retain fragile disk structures that would never survive in clusters. Others remain misshapen, never nudged into symmetry by mergers. These galaxies are fossils of what the universe might look like if cosmic violence were dialed down. But isolation comes with limits. Without a steady supply of fresh gas from filaments or interactions, void galaxies often remain underdeveloped. They rarely reach the grand scales of galaxies like the Milky Way. Many linger as dwarfs, small but stubborn, forming stars at a modest pace for billions of years. Their growth is stunted not by destruction, but by starvation. They are the universe's late bloomers, glowing faintly in emptiness. Not all void galaxies are dwarfs. Surveys have revealed a few surprising giants, large spirals that somehow grew big despite their isolation. One example is NGC 6946, sometimes called the Fireworks Galaxy, perched on the edge of the local void. It is unusually active, producing supernovae at a rate far higher than average. Such cases challenge models of galaxy evolution. How did they grow so large without a dense environment to feed them? Some astronomers suspect they tapped into hidden dark matter filaments, faint bridges that funneled gas into their halos. Others argue they are lucky survivors, remnants of filaments that dissolved as voids expanded. For cosmologists, void galaxies are invaluable because they act as control experiments. In clusters, it's difficult to separate intrinsic galactic evolution from environmental effects. Are galaxies red because they ran out of gas naturally, or because they were stripped by neighbors? In voids, the environment is minimal. Outcast galaxies evolve with little outside interference, revealing the baseline rules of star formation and dark matter dynamics. By comparing them to cluster galaxies, astronomers can measure how much difference the environment really makes. It's both amazing and depressing to think of living in an empty cosmos. Telescopes show that the cosmos is teeming with galaxies, and the night sky on Earth is full of stars. However, your sky would be almost empty if you lived in a vacuum galaxy. A dim scattering of stars would take the place of the Milky Way's majestic band. Even powerful telescopes would see very little beyond your galaxy, only a few smudges separated by unfathomable gulfs. The fact that there are billions of galaxies in the cosmos may be surprising to your culture. The universe would seem empty, limited, and quiet to you. The existence of galactic outcasts proves that even in the harshest deserts, galaxies endure. They may be smaller, lonelier, and slower to grow, but they are survivors. They hold on to their gas, nurture their stars, and light the voids with quiet defiance. For astronomers, they are precious clues. For the universe, they are reminders that life and light can persist even in the deepest emptiness. The quietest zones of space. It's not quite accurate to say that space is silent. The cosmos hums with activity in crowded areas such as galaxy clusters, jets from black holes, X-ray emissions from heated plasma, radio waves from pulsars, and the dim illumination of innumerable stars. There are high-energy particles buzzing and making noise in the intergalactic medium. However, the situation is different inside voids, the enormous underdense areas that make up the majority of cosmic volume. Even the normal background noise of the cosmos seems to diminish in these hollows, which are the quietest places in space. The silence begins with the absence of galaxies. In voids, galaxies are sparse, often separated by tens of millions of light-years. Without crowds of stars, there are fewer supernovae, fewer stellar winds, and fewer jets from active black holes. The typical cosmic signals that fill other regions are reduced to almost nothing. Instead of a bustling symphony of radio and X-ray emissions, voids offer long stretches of emptiness with only the faintest whispers of activity. Measurements confirm this. Radio surveys show that galaxies in voids emit far less radio frequency radiation than their counterparts in clusters. That's because radio signals often come from interactions, galaxies colliding, gas stripping, or central black holes feeding. In isolation, void galaxies evolve more gently, producing weaker signals. This voids some of the radio-quietest places in the observable universe. The same holds for X-rays. Clusters of galaxies glow in X-rays because their intergalactic medium is heated to tens of millions of degrees. Voids, by contrast, lack the mass to generate such hot plasma. Their few galaxies shine, but the vast spaces between them are dark at high energies. Observers looking through a void see not glowing gas, but near total absence. Even gravitational noise is lower. In dense regions, galaxies constantly tug on one another, their motions chaotic. In voids, the gravitational landscape is smoother. Galaxies drift more slowly, their motions dictated by the faint pull of dark matter filaments. The result is a kind of cosmic calm, a place where gravity exerts itself more softly, producing less turbulence. This quietness is not just an absence, it is scientifically useful. Because voids lack clutter, they provide some of the cleanest laboratories for cosmological measurements. For example, the cosmic microwave background, CMB, can be studied more easily through voids, since photons encounter less interference from hot gas or dense structures. Similarly, the faint distortions of gravitational lensing are easier to measure against the calm backdrop of voids, making them ideal testbeds for studying dark matter and dark energy. There's another layer of quiet too, acoustic. In the early universe, sound waves rippled through the hot plasma, leaving imprints we still detect as baryon acoustic oscillations. Today, in dense regions, traces of those ripples are blurred by ongoing interactions. In voids, however, the absence of disruption preserves them more cleanly. It's as if voids have kept a purer memory of the universe's first sounds long after they faded elsewhere. It's odd to picture these peaceful areas. Your equipment would not be able to detect much outside of your solar system if you resided in an empty galaxy. There would be hardly anything in the radio sky. There would be nothing in the X-ray sky. Neighbors' gravitational pull would also be diminished. Your world would seem incredibly quiet, a desert of activity as well as matter. It would be so quiet that you may think your galaxy was the only one in the universe. And yet, this quietness is deceptive. Beneath the silence, voids still hum with the most fundamental signals of reality. Dark matter filaments stretch invisibly, shaping motion. The CMB glows faintly, carrying the story of the Big Bang. Quantum fields fluctuate in the vacuum, producing virtual particles that blink in and out of existence. The void may be quiet compared to clusters, but it is never truly mute. Even in emptiness, physics whispers. This doubles the value of voids for astronomers. They serve as both natural amplifiers of subtle effects and serene testing grounds for hypotheses. Faint signals are lost in loud settings. They can stand out sharply in voids. Void studies are essential to contemporary cosmology because they remove all obstacles and reveal the most nuanced aspects of the cosmos. The edge of the Bootes void. With a diameter of around 330 million light-years, the Bootes void is one of the biggest known hollows in the cosmos. There are barely a few galaxies strewn around its barren interior. The difference at the Bootes void's edge, however, is what really makes it stand out. There is no smooth transition from emptiness to fullness at the border of the vacuum. Abundance takes the place of emptiness in this abrupt wall of galaxies. One of the most striking vistas in the universe is this border between wealth and emptiness. Astronomers first mapped this edge in the 1980s using redshift surveys. They noticed that galaxies seemed to vanish inside a large spherical region but piled up just beyond it. This wasn't an observational illusion, it was real structure. The cosmic web forms in such a way that matter flows out of voids and into surrounding walls and filaments. As a result, void edges become some of the densest galactic neighborhoods, with clusters and superclusters crowding together like cities ringing a desert. The contrast is extreme. Inside the void, galaxies are separated by tens of millions of light-years. Step across the boundary, and suddenly they are packed into clusters, with rich filaments connecting them. It's like walking across an empty wasteland and arriving at a sprawling metropolis without warning. For cosmologists, this sharpness is key evidence of how voids and walls evolve together. The void empties itself by sending matter outward, while the wall grows by accumulating it. The edge of the Bootes void is home to some remarkable structures. Surveys have revealed arcs of galaxies and superclusters curving around its boundary. These include portions of the Bootes supercluster and filaments that extend toward the Hercules corona Borealis Great Wall. In many ways, the edge of the void is more spectacular than the void itself, a cosmic cliff where emptiness meets one of the richest regions of the sky. This transition also shapes the motion of galaxies. Those near the edge feel the push of the void behind them and the pull of the wall in front. The result is a kind of one-way traffic. Galaxies flow outward from the interior and settle into the boundary. Over billions of years, this process sharpens the edge, making it more defined. The Bootes void is not just an empty bubble. It is an engine of motion, constantly evacuating itself and feeding its walls. The physics of this edge offers clues about dark energy. Because voids expand faster than average, the sharpness of their boundaries depends on how strongly dark energy accelerates the universe. By measuring galaxy flows at void edges, astronomers can test cosmological models with surprising precision. The Borealis void, being one of the largest and best mapped, is a crucial laboratory for this work. Imagine residing at the edge of a galaxy. Your night sky would be rich on one side, with thousands of galaxies crammed together to create clusters and bright filaments. You wouldn't see anything on the other side. Hundreds of millions of light-years of nothing but blackness. There would be a cosmic boundary separating plenty from emptiness, creating an extreme contrast. Your galaxy would straddle the line between plenty and emptiness. The edge also reminds us that the universe is a place of extremes. Voids are not just empty, they are defined by the sharpness of what surrounds them. The cosmic web is not smooth or uniform, but jagged, with stark transitions between crowded and barren regions. These edges are the boundaries of the universe's great architecture, the outlines of its cosmic bubbles. These margins will shift as walls shrink and voids widen. Dark energy will cause galaxies to move away, perhaps obfuscating their distinct borders. Today, however, the Borealis void reveals a cosmos that is still refining the distinction between nothing and anything. Cosmic bubbles colliding. Galaxies develop filaments around enormous empty bubbles, giving the large-scale cosmos the appearance of a foam. Like bubbles in soap froth, these cosmic voids grow, change, and occasionally clash instead of merely sitting quietly. The cosmos changes, forming new structures and changing the cosmic emptiness map as voids develop into one another. The universe's architecture is always being rearranged, as the narrative of colliding voids illustrates. The process begins with how voids form. In the early universe, small underdensities expanded faster than average, carving out hollows. Over billions of years, these hollows grew, fed by the flow of matter into surrounding walls and filaments. But voids don't grow in isolation. As neighboring voids expand, their boundaries push against one another. Where they meet, the thin filaments of galaxies that separate them can dissolve, causing the two voids to merge into a larger one. This process, called void percolation, is how smaller voids combine into supervoids hundreds of millions of light-years across. Computer simulations capture this beautifully. In cosmological models, the cosmic web looks like a froth, with voids swelling and occasionally bursting into one another. When they collide, the filaments between them fade, leaving behind a single larger cavity. Over time, the number of small voids decreases while the number of giant ones increases. The universe evolves not just by building galaxies and clusters, but also by letting voids join into vast connected deserts. Observations back this up. Surveys like the Sloan Digital Sky Survey, SDSS, show that voids are not perfectly round, but rather uneven and linked. A lot of them share edges that look thin and worn, which means that accidents are happening. Astronomers have sometimes found long chains of voids that are connected to make huge supervoid complexes. The Borealis void, the Eridanus supervoid, and other voids may have formed by merging many times over the course of cosmic time. The collision of voids doesn't produce explosions or shocks like colliding galaxies. Instead, it quietly reshapes the distribution of matter. As the dividing filaments dissolve, galaxies at the boundary are pulled into denser regions, leaving the void interior even emptier. What remains is a larger, smoother void, with sharper edges where its new boundary lies. It's a silent process, driven not by violence, but by the slow, relentless pull of gravity and the expansion of space. These collisions also affect how galaxies move. As voids merge, their combined gravitational influence changes the flow of matter. Galaxies on the edges may accelerate outward, feeling the push of an even larger underdense region behind them. This contributes to the large-scale streaming motions we observe across the cosmic web, where galaxies drift not only with expansion, but also with the push and pull of void dynamics. Void impacts are an important tool for cosmologists. How merged voids look and how big they are rely on how dark energy works. Astronomers can check if their present models of cosmic acceleration are accurate by watching how voids develop and spread out. It could mean that new physics is at work if voids join faster or in a different way than expected. This could mean that general relativity has been changed, or that dark matter and dark energy are interacting in new ways. Envision two huge empty bubbles that grow until they touch and are each hundreds of millions of light-years across. They don't bounce, instead they join, wiping out the galaxies that were caught on the edge of them. If you lived near the wall that divided the world, the sky would slowly change over billions of years. As time went on, the galaxies that had once marked the cosmic limit would disappear, leaving only empty space. Their world would merge with a bigger desert and be sucked in by the slow-motion clash of nothingness. Vacuum collisions will be the main type of cosmic evolution in the near future, when dark energy speeds up expansion. Spheres and filaments will separate into islands, and voids will join together to form a network of huge hollows that are all linked to each other. In the end, there will only be a few huge voids left, covering most of the universe that we can see. The cosmic web we see now, which is made up of threads and walls, will get thinner until it is only empty. The void as a laboratory. At first look, cosmic voids don't seem to be useful for science. How can you learn anything from places that are almost entirely empty after all? But in the study of the universe, emptiness is just as important as plenty. It turns out that voids are like nature labs, where the rules of physics are very clear to see. Astronomers can test their ideas about dark matter, dark energy, gravity, and even the very beginning of the universe by looking into these huge holes. The key advantage of voids is their simplicity. In galaxy clusters, the environment is chaotic. Thousands of galaxies collide, hot plasma fills the space, and black holes blast out jets. It's hard to untangle cause and effect in such a noisy setting. Voids, by contrast, are quiet. Their few galaxies evolve largely in isolation, unaffected by neighbors. This makes them excellent test cases for studying how galaxies behave when stripped of external influences. For example, void galaxies often retain more hydrogen and continue forming stars long after cluster galaxies have gone dormant. By comparing the two, astronomers can measure how much the environment shapes evolution. Voids also amplify the effects of dark energy. Because they expand faster than average, they are particularly sensitive to the universe's acceleration. Small differences in the properties of dark energy, whether it acts like a cosmological constant or something more exotic, show up more strongly in voids than in dense regions. This makes voids powerful tools for testing cosmological models. By mapping their shapes and growth, researchers can refine estimates of dark energy strength and behavior. An additional advantage is that voids are clear windows to the universe far away. Dense areas have hot gas that spreads and bends light. Since voids are mostly empty, photons can pass through them without much trouble. We can use them to study the cosmic microwave background, CMB, and measure weak gravity lensing because of this. In voids, where light bends, the signal is weaker but easier to understand than in dense groups. In a way, voids remove noise and make the physics behind them more visible. Voids also play a role in testing alternative theories of gravity. Some modified gravity models predict that cosmic structures should behave differently in low-density environments. In dense regions, normal matter and dark matter dominate the signals. But in voids, where there's so little mass, deviations from Einstein's relativity would stand out more sharply. By studying how galaxies move in and around voids, astronomers can put strong constraints on these theories. If void behavior deviates from predictions, it could be the first hint of new physics. On a smaller scale, void galaxies themselves act as miniature laboratories. Because they are isolated, their star formation and chemical evolution proceed slowly, preserving traces of early cosmic conditions. Some may even resemble galaxies from billions of years ago, offering a living glimpse of the past. By measuring their gas content and metallicity, astronomers can reconstruct how galaxies might have evolved without the constant harassment of mergers and stripping. Even the shapes of voids contain information. Most are not perfect spheres, but irregular, elongated cavities. Their alignments and deformations reveal how matter flows across the cosmic web. By analyzing these patterns, cosmologists can measure the universe's expansion rate, test inflationary models, and refine our understanding of how structure grew after the Big Bang. In a sense, every void is a cosmic experiment, its geometry shaped by the laws of physics at work on the largest scales. It's strange to think of voids as labs. We're used to labs being busy places with lots of tools, drugs, and people doing things. On the other hand, voids are places where nothing exists, where quiet and nothingness show truths that are hidden in busier areas. Their power comes from the fact that they don't contain any matter. They get rid of distractions so that minor effects stand out. Voids also teach us that science needs both things that are there and things that aren't there. As much about cosmic development as the galaxies themselves can be learned from the gaps between galaxies. There is order in the world that is made up of both light and darkness, matter and nothingness. Radio silence in the emptiness. The sky is full of action when scientists point their radio telescopes at galaxy clusters. Like cosmic beacons, pulsars send out steady messages. Jets from very large black holes can be heard over millions of light years. Clouds of plasma in space even give off a faint hiss. The story changes, though, when those tools face voids. It's quiet out there in space. There is radio silence in these huge holes because there are no galaxies or events in them. The universe is eerily quiet. Radio waves in space are usually the fingerprints of energetic processes. Star-forming galaxies glow in radio frequencies thanks to synchrotron radiation from supernova remnants. Clusters amplify signals through shocks and turbulence as galaxies collide. Active galactic nuclei light up the sky with colossal radio jets. But voids lack the dense environments that drive these phenomena. With only a handful of isolated galaxies and almost no collisions or mergers, the radio sky in voids is drastically subdued. Surveys confirm this. Data from projects like the NRAO VLA Sky Survey and the LOFAR 2-meter Sky Survey show that galaxies inside voids emit far weaker radio signals compared to their cluster counterparts. Many void galaxies are quiet dwarfs, lacking the massive black holes that power radio-loud jets. Others continue modest star formation, but not at levels that produce strong radio bursts. The result is a stark difference. Clusters roar, voids whisper. This silence makes voids ideal places for testing the background hum of the universe. In crowded regions, the radio sky is cluttered, with foreground emissions masking faint signals. In voids, the absence of strong sources lets astronomers search for the faintest phenomena: primordial hydrogen, weak signals from the early universe, or even hypothetical emissions from dark matter annihilation. In this sense, voids are not just empty, they are clean canvases where subtle cosmic whispers can be heard. One promising line of research involves the 21-centimeter line of neutral hydrogen. This emission, a hallmark of intergalactic gas, is notoriously faint and easily drowned out, but in voids, with fewer competing sources, it becomes easier to detect. By mapping hydrogen in voids, astronomers can trace how gas lingers even in the emptiest places and how it slowly trickles along dark matter filaments. The silence of voids also has consequences for galaxy evolution. Without frequent mergers or active black holes, void galaxies rarely become radio loud. Their isolation preserves them in quieter states, with weak magnetic fields and subdued synchrotron radiation. This explains why void galaxies are often overlooked in radio surveys. They simply don't shine in that part of the spectrum. But their quietness tells a story. It reveals what galaxies look like when stripped of the noise of interactions. What would your radio telescopes pick up if you lived in a galaxy inside another galaxy? It didn't have any pulsar signals from close galaxies, any loud jets from black holes, or a lot of cosmic junk. No matter what you looked at or played, the sky would look empty. It would be one of the quietest places in the universe to live. Still, this quiet is not complete. Radio waves can still pick up the weak hum of the cosmic microwave background. which fills every empty space with a steady signal. Supernovae and a few live galaxies in voids still send out bursts that can be seen from very far away. And changes in quantum mechanics make sure that no part of space is really quiet. But voids are quiet compared to the noise of groups. In the universe, they are like soundproof rooms that block out all sounds but the lightest whispers. For cosmologists, this quietness is a gift. It allows them to study signals otherwise drowned out in busier regions. Searching for primordial hydrogen, mapping faint radio galaxies, or even probing for exotic physics becomes easier in voids. By listening where the universe is quietest, we can learn things impossible to uncover in noisier places. Star formation in exile. When galaxies are close to each other, star creation tends to do well. Collisions and gas flows in and out of clusters and filaments cause bursts of new stars, which power supernovae and bright nebulae. But what happens when a galaxy is tens of millions of light years away from its closest partner and no one can reach it? Even though it doesn't look likely, some of these separated systems are still making stars. Star formation in exile is a rare event that shows how galaxies stay alive in the most isolated parts of the universe. Void galaxies were once assumed to be dormant, with so little access to fresh gas from mergers or cosmic filaments they were expected to wither, their stars aging into quiet redness. Yet observations revealed a surprise. Many void galaxies are not red and dead at all. Instead, they shine blue, evidence of young, hot stars. Even in the deepest deserts of space, they are still igniting new suns. How do they manage it? The key lies in their gas reservoirs. Unlike cluster galaxies, which are stripped of hydrogen by the hot plasma of their environments, void galaxies often keep their gas intact. With no neighbors to steal it, they can slowly recycle their own supplies, turning them into stars at a steady pace. The process is less dramatic than in bustling regions, but far more persistent. Some void galaxies have been forming stars continuously for billions of years, quietly building themselves up in exile. Another factor is their isolation from disruption. In clusters, galaxies are constantly battered by interactions. Collisions that trigger bursts of star formation, but also strip gas and destabilize structures. Void galaxies evolving in peace can retain fragile disks of gas for far longer. This allows them to form stars in a gradual, sustainable way. Their star formation is not explosive but steady, like a candle burning slowly instead of a bonfire flaring briefly. Still, the pace of star formation in voids is modest. These galaxies rarely grow into giants like the Milky Way. Most remain dwarfs or small spirals, producing stars at a fraction of the rate of their clustered counterparts. Their isolation protects them, but it also starves them. They lack the inflows of fresh material that drive major growth. As a result, they evolve slowly, their stellar populations building layer by layer over cosmic time. Surveys like the Sloan Digital Sky Survey have catalogued dozens of void galaxies, and many share intriguing traits. They tend to have high gas-to-star ratios, meaning they have far more hydrogen than visible stars. Some contain enough fuel to keep forming stars for trillions of years, far beyond the lifespan of typical cluster galaxies. In this sense, void galaxies may be the ultimate survivors, continuing to shine long after their crowded cousins have burned out. From the point of view of cosmology, star formation in exile helps test ideas about how galaxies change over time. It shows that the environment is very important. Galaxies in clusters change quickly, becoming bright and then dim quickly, while galaxies in voids change slowly, keeping their resources. This duality explains why galaxies are so different from one another. We might think that all galaxies die and come back to life in bursts if void galaxies didn't stay around. From a human perspective, the idea is haunting but inspiring. Imagine a civilization inside a void galaxy, building its knowledge of the universe. Their telescopes would see almost nothing beyond their home. The cosmic web would be invisible to them, the night sky empty of rich clusters. Yet within their galaxy, stars would still be born, planets would still form, and life could still emerge. They would live in exile, but not in despair. proof that creation endures even in the loneliest places. Some people even think that void galaxies might be home to the last star-forming areas in the very far future. Beyond the cosmic limit, galaxies that are not part of a small cluster will disappear as dark energy speeds up expansion. But void galaxies that are far away and have a lot of gas could keep making stars long after the rest of the universe has gone dark. So, they might not only be people who are still alive in the present, but also the last sparks of the cosmic story. The cold hydrogen reservoirs. Gas is what galaxies need to stay alive. It's needed for stars to form, planets to form, and light to fade over time. A lot of that gas is heated, stripped, or burned up in the hubs of galaxy groups, which is why galaxies are red and cooled. That being said, a different story takes place in the vast cosmic voids, where galaxies are scarce and contacts are few. Astronomers think that there are still huge cold hydrogen reserves hidden in the darkness here. These are thought to be leftovers from the early universe that have been kept safe. Hydrogen is the simplest and most abundant element, forged in the Big Bang itself. In dense regions, it has long since been recycled, pulled into stars, fused into heavier elements, blown out in supernovae, and swept into hot plasma halos. But voids evolve slowly. With fewer galaxies to process it, much of their hydrogen may remain closer to its primordial state, cold and neutral, stretching invisibly through the emptiness. Detecting this hydrogen isn't easy. Neutral hydrogen reveals itself through the 21-centimeter emission line, a faint radio signal caused by tiny flips in the orientation of its electrons. Telescopes like Arecibo, LOFAR, and the upcoming Square Kilometre Array have been used to search for this signal. In voids, the emission is so weak it is nearly drowned out by background noise. Yet hints suggest that cold hydrogen clouds do linger there, unlit by stars and unseen in visible light. These hidden reservoirs may explain how some void galaxies continue forming stars despite their isolation. Unlike cluster galaxies, which are stripped of gas by their environments, void galaxies often retain large amounts of hydrogen. Some even show unusually high gas-to-star ratios, meaning they hold far more fuel than their visible populations suggest. The likely source is these diffuse reservoirs, slowly feeding star formation over billions of years. In fact, void galaxies may be tapping into cosmic filaments of hydrogen that thread invisibly through the voids. Simulations show that dark matter filaments can funnel cold gas into galaxies, even in underdense regions. These filaments are too faint to glow, but their presence may sustain galaxies that would otherwise wither. Without them, star formation in voids might have stopped long ago. The cold hydrogen reservoirs also hold clues about the early universe. Because voids evolve slowly, their gas may preserve conditions closer to the primordial cosmos. By studying its composition, astronomers hope to learn how the first galaxies formed and how matter behaved before heavy elements became widespread. Voids, in this sense, act as time capsules, holding gas that has barely changed in 13 billion years. Another compelling idea is that these pools might be big enough to hold some of the missing baryons in the universe. It has been known for decades by cosmologists that about half of the normal matter that the Big Bang promised doesn't seem to be there. A lot of it probably hides in cosmic gas that is too faint to see directly. A part of this missing matter could be found in voids, which would fill in the blanks in our cosmic inventory with their vast cold hydrogen clouds. Consider floating in the middle of a space that seems to be completely empty. From your point of view, there is nothing there, nothing but dark, though there would be thin wisps of cold hydrogen hiding in that darkness. You would never know they were there. One atom every few cubic meters, floating in the air without making a sound. But over billions of light years, all of those atoms add up to huge pools of space, the void's silent seas. These stores are more than just interesting to cosmologists. They are necessary to improve theories of how galaxies evolve. The amount of gas available directly affects how fast stars grow. If empty galaxies have more hydrogen than we thought, it changes how we think about how being alone affects their growth. It also helps to explain why some space galaxies are still blue and making stars, while other galaxies of the same mass have stopped. It's possible that these cold reservoirs will be the universe's last light sources. As galaxies in dense areas run out of gas and fade away, void galaxies may still be able to make stars from their secret sources, long after the rest of the universe has gone dark. In this way, the universe's deserts may also be its last safe places, where starlight can stay living while it's away. Do voids hide new physics? Some scientists think that cosmic voids could be doors to new physics, even though they look like empty spaces in the universe. These huge holes, which are hundreds of millions of light years across, are not just empty spaces. They are places where gravity, dark matter, and dark energy can be tested in ways that can't be found anywhere else. The rules of the universe may show cracks and even different physics from what we think we know when they are empty. The idea begins with general relativity, Einstein's theory of gravity. Relativity has passed every test in dense regions, from planetary orbits to galaxy clusters. But voids are different. With so little matter inside, they amplify the effects of cosmic expansion. This makes them uniquely sensitive to any deviations from Einstein's equations. If gravity behaves differently on large scales, voids are the places where the discrepancies would show up most clearly. For example, some modified gravity theories, such as FR gravity or scalar tensor models, predict that cosmic structures should evolve differently in underdense regions. Galaxies might move faster, voids might grow larger, or gravitational lensing might bend light less strongly than expected. By mapping voids with surveys like the Sloan Digital Sky Survey and the Dark Energy Survey, astronomers can test these predictions. So far, relativity holds, but the data are still young. The possibility that voids could expose cracks in our theories keeps researchers watching closely. Voids are also crucial for probing dark energy, the mysterious force accelerating the expansion of the universe. Because voids expand faster than average, their shapes and growth rates are directly tied to dark energy's properties. Some models suggest that if dark energy evolves over time, or if it interacts with dark matter, the effects would be most obvious in voids. Measuring the ellipticity of voids, their alignment with the cosmic web, and their impact on the cosmic microwave background could reveal whether dark energy is truly a cosmological constant or something stranger. Then there are the puzzles that standard physics struggles to explain. The CMB cold spot, for example, lines up with the Eridanus supervoid, but seems deeper than void physics alone can account for. Could it be a sign of exotic phenomena, like a collision with another universe or a large-scale defect in space-time? Most cosmologists remain cautious, preferring simpler explanations. Yet the fact that such anomalies often appear in connection with voids keeps the speculation alive. Voids may also play a role in the hunt for the nature of dark matter. If dark matter is made of exotic particles, their behavior in low-density environments could differ from dense regions. For instance, if dark matter can self-interact, it might leave subtle imprints on void galaxy distribution or lensing signals. Some even propose that voids could help test warm dark matter models, where particles move faster than in cold dark matter scenarios, altering small-scale structure inside voids. The appeal of voids as laboratories is that they remove the noise. In clusters, too many factors, hot plasma, mergers, feedback from black holes, muddy the signals. In voids, things are simpler. If you see a deviation in void dynamics, it's harder to blame on local chaos and easier to attribute to fundamental physics. That clarity makes them attractive for testing hypotheses that might otherwise remain abstract. The idea that the universe's darkest nothingness might be where its biggest secrets are hidden is creepy from our point of view. Imagine that you are floating in the middle of nothingness. You can't see anything. Something could be changing the laws of gravity, though, and space-time would be stretched in ways we don't fully understand yet. There's a chance that the void's silence isn't as quiet as it seems. They could be where the universe whispers its deepest secrets. Still, it's important to be cautious. Many supposed anomalies have faded as data improved. The cold spot, once hailed as a sign of exotic physics, may turn out to be partly statistical. Voids may ultimately confirm the strength of relativity and dark energy, rather than overthrow them. But that's the nature of science. You look where the theories are most vulnerable, and voids are exactly those places. Cosmic acceleration traced in voids. Dark energy is one of the most puzzling things in the study of the universe. We know that it speeds up the growth of the universe, but we don't know what it is. Astronomers look at the voids in addition to galaxies and clusters to determine the effects of this phenomenon. For cosmic acceleration, these huge areas of low density work like magnifying glasses. As experts follow the forms and movements of voids, they can see how dark energy changes the universe. The logic is simple. In dense regions, gravity resists expansion. Clusters pull galaxies inward, countering dark energy's push. But in voids, where matter is scarce, gravity offers little resistance. This means voids expand faster than the universe as a whole, exaggerating the influence of dark energy. By studying voids, scientists see the acceleration not diluted but amplified, making it easier to measure. Researchers look at the shapes of voids as one way to do this. Voids would appear roughly circular if the universe were growing evenly in all directions. But voids often look stretched along the line of sight because dark energy and expansion work together. This shift is called the Alcock-Podzinski effect, and it gives us a straight way to figure out how fast the universe is expanding. This method has been used by the Sloan Digital Sky Survey and other projects to prove that voids really do store dark energy's effects. Galaxy movements are another way to look at it. Galaxies near the edges of voids don't just stand there. The underdensity of the space pushes them away. Astronomers can figure out how fast voids grow by making maps of these flows. The results are the same as what models with dark energy said would happen. But the behavior of voids is some of the best evidence for cosmic acceleration that doesn't come from clusters or supernovae. Dark energy and voids are linked in a deeper way. Simulations show that even small changes in the features of dark energy leave clear marks in voids, whether it stays the same, changes, or interacts with dark matter. Some models say that voids should be bigger or more empty, while others say that they should have longer shapes. Cosmologists can rule out whole groups of dark energy ideas by comparing real poles to these predictions. Voids act as cosmic judges in this way, measuring not only the rate of growth, but also the physics that makes it happen. The Dark Energy Survey, which has laid out thousands of voids over billions of light years, is one striking example. Researchers proved that voids accurately show the rapid growth by stacking them and looking at how they changed shape. The combination of these data, with those from supernova studies and baryon acoustic waves, creates a cross-check that makes the dark energy model more reliable. Picture yourself in a galaxy with no other stars or planets and seeing your friend slowly move away. There would be more empty space around you than anywhere else, which would pull the sky apart faster. For your society, the speeding up of the world would not be a vague idea. It would be written on the sky right now. You would see the universe growing faster than people who live in areas with more people. It wouldn't just be empty around you, it would be the timekeeper for the fate of the world. Yet, as precise as void studies are, they also highlight how much we still don't know. Dark energy could be a simple cosmological constant, a property of space-time itself, or it could be something dynamic, tied to new fields or forces. Voids can help distinguish between these possibilities, but so far, the evidence still points to the simplest model. Whether this is the true explanation or just an approximation remains one of the great questions of modern physics. Voids are beautiful because they make us question our presumptions. At first glance, they look like they're not useful, empty, lifeless, and unimportant. But the fact that they are empty makes them strong. They get rid of things that are in the way, which makes dark energy stronger in a way that crowded places can't. We can see the force that shapes everything by measuring nothingness. Voids in computer simulations. Because cosmic voids are so big and empty, it might seem difficult to learn more about them. How can you map something that isn't there after all? Supercomputers can duplicate the universe from its earliest days and track billions of bits of matter and dark matter as they change over billions of years. This is where the answer lies. These models have turned into useful places to study voids, showing how nothingness itself grows, merges, and changes the universe. The foundation of these simulations is the LCDM model, lambda cold dark matter, which combines dark energy, lambda, with cold dark matter to describe cosmic evolution. In this model, tiny quantum fluctuations in the early universe grew into the large-scale structures we see today: galaxies, filaments, clusters, and voids. By inputting the initial conditions and letting gravity, expansion, and dark energy play out, simulations reproduce a universe strikingly similar to the one we observe. Voids naturally emerge in these models. As matter flows towards denser regions, underdense patches expand faster, emptying themselves out. Over time, small voids merge into larger ones, forming the vast hollows seen in galaxy surveys. Simulations show this process with breathtaking clarity, producing cosmic webs that match observations from the Sloan Digital Sky Survey and other deep maps of the sky. One of the best-known projects is the Millennium Simulation, which followed the evolution of 10 billion particles of dark matter across a cube of space more than 2 billion light-years wide. In its output, voids stretch like enormous bubbles, surrounded by filaments and clusters. Later projects like Illustris and Eagle added baryonic matter, gas, stars, and black holes, allowing astronomers to see how void galaxies evolve in these environments. The result: models that not only reproduce voids but also predict their galaxy populations, gas content, and shapes. Simulations are crucial because they let researchers test hypotheses impossible to observe directly. For example, they can alter the laws of gravity, change the nature of dark matter, or remove dark energy altogether, then watch how voids behave. If voids grow too slowly, too quickly, or into the wrong shapes, the model can be ruled out. In this way, voids serve as cosmic referees, telling us which theories survive and which fail. The way voids percolate and merge, like bubbles in foam, is an interesting thing that scientists have learned from models. As thin threads between them dissolve, small voids combine to form supervoids. This fits with what we know about how the biggest voids aren't made up of a single structure, but rather a network of smaller ones that are sewn together. Also, simulations show that voids are not completely empty. They are full of faint strands of dark matter and rare galaxies, most of the time dwarf galaxies that can live in the desert. Without computer tests, it would be impossible to guess these facts. Another breakthrough comes from studying void shapes. In simulations, voids are rarely spherical. Instead, they stretch and distort depending on the surrounding cosmic web. Their alignments reveal how matter flows and how expansion interacts with gravity. Comparing these simulated shapes with real surveys allows astronomers to measure dark energy's effects and test general relativity on the largest scales. Simulations even help explain anomalies like the CMB cold spot. By creating virtual universes, researchers can ask how often voids of a certain size or depth appear. If supervoids as large as Eridanus are rare in simulations, then their presence in reality may point to unusual physics, or simply to a statistical outlier. Either way, simulations provide the baseline against which reality is compared. The pictures that these programs make are mind-blowing. In them, threads of galaxies weave around huge black holes to make the universe look almost living. Seeing the cosmic web change on a computer screen is like seeing the world breathe, grow, and stretch out over billions of years. The voids don't stay the same. They grow, join, and move, slowly changing the shape of the universe. As poles get more in-depth, models will become even more important. Galactic voids will be shown with a level of accuracy that has never been seen before, thanks to projects like the Euclid mission and the Vera C. Rubin Observatory. To make sense of that data, simulations will be needed to connect what was seen and what was thought. They connect what we see in the sky to the laws of physics we think rule the universe. The largest known supervoids, Scholars were shocked by how big cosmic voids were when they first found them. But as studies went deeper into the universe, they found something even more amazing. Supervoids, which are empty spaces that are hundreds of millions to billions of light-years across. These huge deserts in space are some of the biggest structures that have ever been seen. They are on par with the big walls and filaments in terms of how they shape the cosmic web. One of the most famous is the Boutte's void, discovered in 1981. At 330 million light-years wide, it was the first void large enough to capture public imagination. Yet compared to the true giants, it is modest. The Eridanus supervoid, associated with the mysterious cold spot in the cosmic microwave background, is nearly 1.8 billion light-years across. To put that in perspective, light would take almost 2 billion years to travel from one side to the other, longer than complex life has existed on Earth. Other supervoids have been catalogued by surveys like the Sloan Digital Sky Survey and the Dark Energy Survey. Many of them stretch between 500 million and 1 billion light-years wide. They are not isolated spheres, but sprawling, irregular cavities stitched together from smaller voids. These structures often connect into chains, forming immense networks of emptiness embedded in the cosmic foam. Supervoids are important because their size makes them powerful laboratories for cosmology. Their rapid expansion amplifies the effects of dark energy, making them key testbeds for measuring the universe's acceleration. Their enormous gravitational underdensities also leave imprints on the cosmic microwave background, producing faint cold spots detectable with sensitive satellites. By studying supervoids, astronomers can probe both the early and present-day universe in a single structure. An issue that is still being talked about is how common these giants really are. Supervoids of 1 billion light-years or more are not common in models of the standard cosmic model, but they can happen. For example, the Eridanus supervoid is at the very end of what people think should happen, which makes it a useful oddity. It could mean that dark energy has changed, or that there are other ways for structures to form if future studies show that these huge voids are more common than thought. Supervoids also shape the behavior of galaxies along their edges. Because matter flows out of them, their boundaries often contain some of the densest walls and filaments in the universe. Galaxies caught at these borders are pulled into clusters, leaving the interiors barren. For astronomers, this creates a dramatic contrast, the sharp transition from rich galactic highways to near total emptiness. It is a landscape on a scale almost impossible to comprehend. Picture yourself standing in the middle of a galaxy. The people closest to you would be hundreds of millions of light-years away, which is very, very far away. A few dim galaxies would be the only things that could be seen in the night sky. The universe would seem dead to your society, because its riches would be far away, out in the distance, where you could never reach them. You would be living in one of the most lonely places in the world. In a strange way, though, these voids might also be the best places to test the basic rules of nature. Some of the noise that makes measures hard to make in busy areas is taken away by these areas because they're so empty. Scientists can use them to study how dark matter and dark energy work together, how gravity bends light, and how the growth of the universe changes over time. That's right, supervoids are like deserts, but they're better places to find the truth. As technology improves, we are likely to discover even larger voids. Projects like the Euclid mission and the Vera C. Rubin Observatory will map billions of galaxies, tracing the cosmic web at unprecedented scales. It is entirely possible that we will find supervoids wider than 2 billion light-years, structures so vast they challenge our definitions of what a structure even means. The far future of voids. We can already see voids that are hundreds of millions or even billions of light-years wide, but their story isn't over yet. The universe will keep growing because of dark energy, and voids will get even bigger. In the very far future, they will completely control the world, leaving behind a place where nothing but nothingness is present. The key lies in how voids interact with dark energy. In dense regions, gravity holds galaxies together in clusters and filaments, resisting the pull of expansion. But in voids where matter is scarce, nothing counters dark energy's push. This imbalance means that voids expand faster than the universe overall. Over billions of years, they eat into the surrounding structures, stretching their boundaries and swallowing what remains of filaments and smaller galaxies. Simulations show that as time goes on, clusters will shrink into isolated islands, while voids inflate into nearly all-consuming seas. Right now, voids occupy about 80% of the universe's volume. In the future, that fraction will approach 100%. The cosmic web will thin, leaving just a few scattered knots of galaxies surrounded by an ocean of emptiness. The local group, home to the Milky Way and Andromeda, will merge into a single elliptical galaxy over the next few 100 billion years. But beyond that island of stars, the local void will expand relentlessly, pulling everything else beyond reach. Distant galaxies will slip across our cosmic horizon, vanishing not because they've ceased to exist, but because their light can no longer catch up to the accelerating expansion. From our perspective, the universe will shrink to darkness. Voids will not only grow, they will isolate. Civilizations in the far future will look out into the sky and see nothing but their own galaxy. They will have no evidence of the cosmic web, no proof that billions of galaxies once filled the cosmos. For them, the universe will seem static and lonely, with no hint of the great structures that once existed. The cosmic truth we know today will be hidden by the expansion of voids. This isolation also spells the end for cosmic archaeology. Right now, astronomers use the large-scale distribution of galaxies to test cosmology and trace back to the Big Bang. In the far future, those markers will be gone. The evidence will be erased by expansion, leaving voids as the only dominant structure. The record of the universe's history will fade into silence. The process will not stop there. As trillions of years pass, star formation itself will dwindle. Even galaxies that survive in islands will eventually burn through their fuel. The cold hydrogen reservoirs that sustain void galaxies today will run out. Stars will fade, leaving behind only white dwarfs, neutron stars, and black holes. The voids will keep expanding, but the galaxies within them will go dark. The universe will enter its degenerate era, when light itself becomes rare. In the end, voids will be the universe itself, not just the empty space between galaxies. Beyond the borders, clusters will vanish, galaxies will turn black, and the last traces of sunlight will be gone. The sky will be almost empty, with only the pull of dark matter and the quiet hum of black holes breaking apart to break up the sound. This picture of the future is one of the scariest ones I've ever seen. One day, the night sky we see every night, full of stars and galaxies, will be gone. In the future, people will not see the void as something far away, but as the very structure of reality. Their world will be nothing, and the only thing that will surround them will be quiet. And yet, there is a strange beauty in this fate. The voids, once thought to be gaps or mistakes in the cosmic web, turn out to be the universe's final destiny. They are not interruptions but endpoints, the culmination of billions of years of expansion. The far future of voids is the far future of the cosmos itself, a universe where nothingness reigns and the story of light has closed. The loneliness of future astronomers. These days, astronomy is a very rich field of study. Telescopes can take pictures of thousands of galaxies at once, map bands that stretch hundreds of millions of light years, and look into the Big Bang's faint glow. The night sky is full of signs that show how big and long the universe is. However, scientists will encounter a very different world in the far future, after trillions of years of cosmic expansion. They will no longer think that the universe is big and full of things. It will look small, nearby, and very lonely. The culprit is dark energy. As it accelerates expansion, galaxies outside of local clusters are receding faster and faster. Already, many are moving away at speeds greater than light relative to us, making them unreachable forever. In tens of billions of years, the cosmic horizon will shrink so much that only our local group of galaxies, by then merged into a single elliptical Milkomeda, will remain visible. Everything else will have slipped beyond detection. Future astronomers will peer into their skies and see only one galaxy. Their telescopes will detect no filaments, no clusters, no cosmic web. To them, the universe will seem static, a lonely island floating in emptiness. The evidence that billions of galaxies once filled the cosmos will be gone. They will live in the middle of a void so vast that even the concept of a larger universe may seem absurd. This raises a profound irony. We, alive today, exist in a privileged moment. Our telescopes can still see billions of galaxies, map the cosmic microwave background, and measure the acceleration of expansion. We know we live in a universe shaped by voids and filaments. But astronomers in the far future will not have that luxury. Their observations will suggest a small, eternal cosmos centered on their one galaxy. Without fossil records like the CMB, they will have no way to reconstruct the true story. The void will have erased it all. Some scientists call this the end of cosmology. Right now we can study the Big Bang, inflation, dark matter, and dark energy because we still see their signatures across the sky. In trillions of years, those signatures will fade. The CMB will redshift so far into long wavelengths that no conceivable detector could measure it. Voids will expand until only a handful of structures remain. Future astronomers will be blind to the universe's history, trapped in an observational prison built by dark energy. Think how lonely those scientists must have been. Imagine looking through a telescope at the stars at night and seeing nothing. There were no dim lines of clusters or smudges of galaxies far away. There was only blackness. That's all you'd know, and the sky would be a shell of quiet. You might wonder if the universe has always been so empty, or if it has ever been bigger. Without proof, you might come to the second conclusion. The rules that made the universe would hide the big secret of the universe. This scenario highlights just how fragile our knowledge is. We take for granted that we can see the cosmic web, but this is a temporary gift. The universe is revealing itself to us now in a way it never will again. We are living in the one era when voids, filaments, and galaxies are still visible. In the deep future, the void will win, and the story will be buried beneath silence. But there is also a strange beauty here. Astronomers in the future will not understand the world we see, but they will still enjoy gazing at the stars in their own galaxy. They won't be able to measure the voids, but they will still live there. Being alone in their universe won't make them less curious. It will just change how they look at things. They will come up with their own questions, and the nothingness around them will shape the solutions they give. The fact that future scientists will be alone is not only a problem for them, but also a warning for us. It serves as a constant reminder of how rare and valuable this time in cosmic history is. There are still voids we can plan out before they are gone forever, and we can still see the whole universe. We are on the edge of what we know, and that won't last forever. The cold silence of entropy. The world is getting older, not just bigger. As galaxies crash into each other, stars burn, black holes eat, and the universe moves closer to its end state, equilibrium. Entropy, the tendency for systems to develop toward chaos and uniformity, is a term used in physics to describe this process. As a cosmic concept, entropy points to a time when the world will be perfectly balanced and nothing new will be able to happen. These things are already going to happen in the cosmic voids more than anywhere else. Voids are the quiet previews of entropy's rule. Inside them, star formation is rare, collisions are scarce, and energetic events almost never occur. The galaxies that do exist there evolve slowly, faintly burning through their gas without replenishment. Compared to the bustling chaos of clusters, voids are calm, still, and subdued, small-scale echoes of the heat death that awaits the entire universe. Entropy grows because energy spreads out. A hot star radiates until its warmth diffuses across space. A black hole emits Hawking radiation until it fades. Galaxies exchange gas and stars until they settle into stability. In dense regions, this process is noisy. Supernovae explode. Quasars flare. Clusters collide. But in voids, entropy's march is quiet. There, energy is already thinly spread. and the silence feels like the future seeping into the present. Cosmologists describe the universe's ultimate fate as the heat death, though the term is misleading. It doesn't mean the universe will be hot. It means all energy will eventually be evenly distributed, so no gradients remain to fuel change. Stars will fade, black holes will evaporate, and motion will cease. The cosmos will become an expanse of cold darkness where entropy is maximized. Voids give us a glimpse of that destiny today, because they are already closer to equilibrium than anywhere else. Observations confirm this eerie foreshadowing. Voids have lower temperatures than clusters, not just in their galaxies, but in their cosmic microwave background shadows. Photons lose energy passing through expanding voids, leaving cooler imprints on the sky. These cold patches are like fingerprints of entropy's approach, showing that in emptiness, energy is already dissipating faster. Think about living in a galaxy with no stars trillions of years from now. The world you live in might still have lights and get power from dying stars, but the rest of the universe would be quiet. There are no new galaxies to look at, no supernovae to record, and no cosmic action at all. Chaos would be all around you, and the sky would be black with only the faint glow of your own stars to break the calm. Still, there is a strange beauty in the fact that chaos will always happen. There is one rule that can't be broken. Entropy will always be there, no matter what science lies beyond dark matter and dark energy. Voids make this very clear. They slowly get emptier, stiller, and quieter. They are not mistakes made by God. They are what all structures do naturally. For scientists, voids offer a way to study entropy in action. By measuring how gas cools in isolation, how galaxies slowly fade without interactions, and how radiation dissipates across expanding hollows, astronomers can see the mechanics of cosmic aging. The lessons we learn from voids today will help us understand what the universe will look like in tens of trillions of years. People often think of black holes as engines that run forever, but they can't stop chaos forever. They will get smaller and smaller until they disappear in the far future, leaving only empty space behind. Not only will voids grow, they will also take in everything until nothing is left but nothingness. The sound we hear in voids right now will one day be the music of the whole universe. Entropy's cold quiet is not a tragedy, it is the truth. The universe wasn't made to last forever, it's meant to change, and the last change is silence. Voids help us remember that. They are the early parts of the ending of the story, where chaos already rules. Cosmic archaeology in the empty. At first glance, it looks like cosmic voids are the worst places to look for past. They are quiet, empty, and lacking in galaxies. But in a strange way, the fact that they are empty makes them important. The slow rate of development in voids keeps things more like they were in the beginning of the universe. Astronomers use these places for cosmic archaeology, which is a way to find old signs that are lost or changed in busy areas. In clusters and filaments, galaxies collide and merge constantly. These interactions accelerate evolution, transforming spirals into ellipticals, stripping gas, and enriching stars with heavy elements. The record of the past is muddied by countless disruptions, but void galaxies, stranded in isolation, evolve differently. They grow slowly with fewer mergers and less external influence. As a result, they act like time capsules, keeping features that galaxies in denser regions have long since lost. A good instance is their metallicity, which means they have a lot of elements heavier than helium. In groups, galaxies quickly get better as new stars are born and supernovae explode. The process is slow in voids, though. A lot of void galaxies still don't have many metals, making them look like galaxies from billions of years ago. Astronomers can get a hint of what the universe's first galaxies might have looked like by studying the chemicals that make them up. Voids also preserve gas reservoirs more faithfully. In crowded environments, galaxies are stripped of hydrogen by interactions or heated by cluster plasma. In voids, gas often survives untouched, allowing galaxies to form stars steadily over cosmic timescales. Some void galaxies even show unusually high gas-to-star ratios, hinting at supplies that stretch back to the early universe. This gas is like a fossil of creation itself, pristine, cold, and ancient. Even the shapes of void galaxies hold clues. While cluster galaxies are reshaped by mergers, void galaxies often remain irregular or fragile spirals. Their forms reflect natural evolution without constant interference, helping astronomers separate what comes from internal processes versus external environments. In this way, void galaxies act as control samples in the experiment of cosmic evolution. Beyond galaxies, voids themselves preserve ancient information. Their size distribution and shapes reflect the initial conditions of the universe. Tiny density ripples imprinted during inflation grew into the web of voids and filaments we see today. By mapping void statistics, cosmologists can test models of inflation and measure parameters like the amount of dark matter and the strength of dark energy. The emptiness carries a memory of the beginning, written in its structure. The cosmic microwave background, CMB, also leaves a mark in voids. As photons pass through, they lose energy in ways that depend on the void's expansion. These subtle shadows provide archaeologists of the cosmos with clues about how voids have grown since the universe was young. They are faint, but they are fossils nonetheless, imprints of processes that began nearly 14 billion years ago. It's scary to think about digging in nothingness. Archaeologists dig through ruins on Earth to find items from long-ago societies. Astronomers search through cosmic voids in search of artifacts from the past. There aren't any broken pots or stone tools here, though. Instead, there are chemical abundances, galaxy forms, and the faint whispers of photons. The void is not empty. It is an exhibit of the history of the universe that is kept silent. Surveys in the future will make this picture clearer. The Vera C. Rubin Observatory, Euclid, and the Square Kilometre Array will make maps of voids that are more accurate than ever before. They will be able to trace the structures of voids and look into their galaxies in great detail. Scientists will be able to improve their understanding of the timeline of cosmic evolution by checking to see if our models of galaxy growth and dark energy match up with the records that have been kept in the voids. Voids change what we think we know. We think of them as empty, but they are full of useful data. The gas in their galaxies comes from the beginning of the universe, and their structure is a frozen copy of the beginning of the universe. They are the places where history stays for a long time without being changed by cosmic noise. When nothing becomes everything, people often think of the universe as a sea of galaxies that goes on forever across the night sky. But this picture isn't accurate. At the biggest sizes, galaxies are just dots, filaments are just threads, and clusters are just knots tied along the edges of a background that is mostly empty. When it comes to bulk, voids already make up most of the world. There is no doubt about the paradox. When you use space to measure the universe instead of light, what is nothing becomes everything. Today, voids occupy more than 80% of the universe's volume. They are not rare bubbles between filaments. They are the universe's true foundation. Galaxies, stars, and planets exist in thin walls wrapped around these hollows, like dew clinging to a spiderweb. The vast majority of the cosmos is not matter but emptiness. It is not the light that defines the large-scale structure. It is the darkness. This reality reshapes how we think about existence. From Earth, the Milky Way looks like a grand structure, immense and full of stars. Yet compared to the nearby local void, it is a tiny borderland, clinging to the edge of emptiness. Multiply that picture across the universe, and the truth emerges. Most galaxies are not in the middle of anything. They are on the margins of nothing. The dominance of voids also explains the universe's foam-like architecture. Clusters and filaments are not scattered randomly. They form where the walls of multiple voids meet. Matter flows out of voids into these boundaries, sharpening them while hollowing the interiors further. In this sense, galaxies exist not because of their own gravity alone, but because emptiness has pushed them together. The universe is sculpted as much by voids as by matter. From a cosmological perspective, this is crucial. It means that studying voids is not optional, it is essential. If voids dominate the volume, then they dominate the geometry, the dynamics, and the future of the cosmos. Dark energy accelerates expansion most clearly in voids. Gravitational distortions stand out most cleanly in voids, and the imprint of inflation is preserved most faithfully in voids. Nothingness is not a background. It is the stage on which everything else plays out. As the universe evolves, this dominance will only increase. Dark energy ensures that voids expand faster than walls or clusters. Over billions of years, filaments will thin, clusters will isolate, and galaxies will vanish over the cosmic horizon. The percentage of space occupied by voids will climb toward 100%. Eventually, matter will be reduced to rare islands floating in an ocean of dark, endless nothing. The cosmic story is one where emptiness wins. For astronomers, the phrase, "when nothing becomes everything," is not just poetic, it is literal. Voids are where the universe spends most of its volume, most of its expansion, and most of its time. Our focus on galaxies reflects human bias. We see light, so we think light defines reality. But the deeper truth is that the universe is mostly dark, and that darkness is not secondary. It is the dominant feature of existence. We like to imagine that we live in a universe full of stars, but the truth is that we live on the thin film between voids, on the surface of nothingness. The vastness of the universe is not what it has, but what it doesn't have. The voids are not just empty spaces between galaxies, they are the universe itself, with galaxies just adding to the look. This point of view also brings up philosophical issues. If nothing rules over everything, then maybe something is more basic than nothing. The framework of the universe doesn't come from matter being there, it comes from matter not being there. Galaxies are just afterthoughts, formed and limited by the vast voids that are growing all around us. In a real way, we were born on the shores of naught and are children of the void. The eternal darkness ahead. Light coming into the world, spreading out, and then going out is the story of the universe. As galaxies crash into each other, stars explode, and black holes roar, but eventually everything goes dark. The voids, those huge holes that already fill the universe, are the clearest places where this fate is written. They are glimpses of nothingness now, but in the far future, they will be everything. Galactic voids, not galaxies, make up the last part of the universe. It will always be dark ahead. Dark energy ensures this outcome. By accelerating cosmic expansion, it drives galaxies farther apart, stretching voids faster than dense regions can resist. Over the next hundreds of billions of years, clusters will isolate into lonely islands. Beyond them, the voids will swell, merging into a single connected ocean of emptiness. From any vantage point, the night sky will shrink until only the stars of one local cluster remain. Everything else will have disappeared beyond the cosmic horizon. In that distant future, star formation will grind to a halt. Gas supplies will dwindle, leaving only old stars to burn through their final fuel. Red dwarfs will glow faintly for trillions of years, but eventually they too will fade. Galaxies will dim into collections of dead embers, white dwarfs, neutron stars, and black holes. The voids will no longer be empty spaces between galaxies. They will be the universe itself, with rare oases of dark remnants scattered across them. Even black holes, the last great engines, cannot resist forever. Through Hawking radiation, they will slowly evaporate over unimaginable spans of time. Supermassive black holes may take 100 trillion years to fade, but fade they will. When they vanish, nothing will remain to puncture the silence. The universe will be reduced to thin radiation stretched across expanding voids. This is the heat death, a cosmos at maximum entropy, where no gradients exist to drive change. No new stars will form, no galaxies will collide, no black holes will feed. The voids will expand until they fill everything, and the silence will be absolute. It will not be an explosion or a collapse, but a slow surrender to nothingness. The world we live in is full of light. The Milky Way shines in the sky. Millions of galaxies can be seen through telescopes. The universe is full of exciting things, like supernovae, pulsars, and quasars. Imagine that everything is gone, that nothingness has erased everything. That is the deepest loneliness you can imagine. There isn't just physical darkness ahead, there is psychological darkness as well. It's the end of all star stories ever written. But there is also something strangely beautiful about this fate. The voids are not mistakes in the universe, they are its plan. They show the inevitable end of growth, which is what Entropy's law says should happen. This world is not going to end in fire or crash. It is going to end in quiet. For it is going back to the same silence from which it came. Experts today are lucky to know these things. Because we live in this time in cosmic history, we can still see the universe as a whole. The voids can be mapped, the filaments can be tracked, and the afterglow of the Big Bang can be measured. People in the future won't be able to do this. Their skies will be empty because of growth, so they will only see darkness. But now we can see both how rich galaxies are and how empty they will be when they die. The eternal darkness ahead is not a tragedy, it is a truth. The cosmos is not designed for permanence, it is designed for change, and its final change is silence. Voids remind us of that destiny. They show us not just the absence of matter, but the direction of time itself, toward emptiness, toward equilibrium, toward the end. The universe, once alive with fire and light, is drifting towards silence. The voids that surround us today are not just empty, they are previews of tomorrow, the shape of what the cosmos will become. One day, only darkness will remain, and the story of galaxies will be gone. But here and now, we can still glimpse the beauty, the terror, and the wonder of that destiny. If you want to keep exploring the mysteries of time, space, and the fate of everything, please subscribe, like, and comment to Beyond Horizons, because together we'll keep searching for light even at the edge of the void.